Bell's theorem paradox. Imagine two particles created at the same point and traveling in opposite directions. According to classical physics, the behavior of each particle should be determined by local causes, meaning that any measurement made on one particle would immediately influence the other, but only through some form of local interaction. But what if I told you that quantum mechanics suggests something far more mysterious? In the Bell's theorem paradox, we encounter a phenomenon called quantum non-locality, where the measurement of one particle's properties seems to instantaneously affect the measurement of the other particle, even if they are light years apart. How can two particles, separated by vast distances, influence each other faster than the speed of light, seemingly violating the principle of locality? This paradox stems from John Bell's theorem, which shows that local hidden variable theories cannot explain the correlations observed in quantum experiments, forcing us to accept the non-local nature of reality. If quantum mechanics is correct, then the very fabric of reality is fundamentally different from anything we can intuitively grasp. Let's explore the Bell's theorem paradox, where quantum entanglement, locality, and the nature of information collide in a profound challenge to our understanding of the universe. The Bell's theorem paradox is based on John Bell's groundbreaking work in the early 1960s. Bell, a physicist working in the field of quantum mechanics, developed a theorem that aimed to resolve a fundamental debate about the nature of quantum mechanics, particularly regarding the idea of hidden variables. Hidden variable theories suggest that particles have properties that are determined by some underlying set of variables that are not directly observable, and that these properties should determine the outcomes of quantum measurements in a local manner. In other words, the measurement outcomes of particles should only be influenced by local causes within their immediate vicinity. Bell's theorem, published in 1964, showed that no local hidden variable theory could reproduce all the predictions of quantum mechanics. Specifically, he showed that quantum entanglement, the phenomenon where particles become correlated in ways that defy classical expectations, implies the existence of non-local interactions. According to quantum theory, the measurement of one entangled particle's properties instantaneously affects the state of the other particle, regardless of the distance between them. Bell's theorem demonstrated that the predictions of quantum mechanics are incompatible with the idea that physical reality can be explained by local hidden variables. This led to the Bell's inequality, an experimental test that could distinguish between quantum mechanics and hidden variable theories. Subsequent experiments, such as those by Alain Aspect in the 1980s, have consistently confirmed the non-local nature of quantum entanglement, providing strong evidence for Bell's conclusions and challenging our understanding of locality and reality. The Bell's theorem paradox is a profound challenge to our classical intuitions about the nature of reality. It reveals that the predictions of quantum mechanics cannot be explained by any theory that assumes local hidden variables, i.e., that the properties of particles are determined by factors that are hidden from view but are localized in space and time. The paradox underscores the non-local nature of quantum mechanics, where entangled particles appear to affect each other's states instantaneously, no matter how far apart they are. This phenomenon challenges our traditional understanding of space, time, and causality. To understand the paradox, we must break down Bell's theorem, quantum entanglement, and the experimental tests that have confirmed the non-local behavior of quantum particles. 1. Classical physics and hidden variables. A. Locality in classical physics. In classical physics, we are accustomed to the idea that objects and particles exist in a well-defined state that is determined by local causes. When we measure a property of a particle, such as its position or velocity, the outcome of that measurement is determined by the particle's previous history and the conditions of its immediate surroundings. This is called local realism, the idea that physical properties of objects exist independently of observation and that interactions are limited to local effects that obey causal relationships. For example, if we measure the position of a particle, we assume that its location is already determined by the interactions it has had in its immediate environment. This intuition underpins much of classical physics, where locality and determinism govern the behavior of particles. B. Hidden variables and local theories. In the early days of quantum mechanics, some physicists, including Albert Einstein, proposed the idea of hidden variables, unobservable factors that could explain the probabilistic nature of quantum measurements. According to this view, the uncertainty and indeterminacy in quantum mechanics would be the result of missing information about the system. And if we had access to the right hidden variables, we could predict the outcome of quantum measurements with certainty. This would restore a sense of determinism to the quantum world. Local hidden variable theories suggested that the outcome of a quantum measurement should be determined by local factors in the particle's environment, without needing to involve non-local influences. However, this classical view would be contradicted by the predictions of quantum mechanics, as we shall see. 2. The foundations of Bell's theorem A. Quantum entanglement and non-locality. The paradox at the heart of Bell's theorem arises from the phenomenon of quantum entanglement, where two particles become correlated in such a way that the properties of one particle are instantaneously linked to the properties of the other, no matter how far apart they are. According to quantum mechanics, the state of an entangled system cannot be described by the properties of individual particles. Instead, the particles must be described by a joint wave function that accounts for their interconnectedness. For example, if two particles are entangled in such a way that their spins are correlated, measuring the spin of one particle will instantly determine the spin of the other, even if they are separated by vast distances. This instantaneous correlation occurs regardless of the time it takes for light or any signal to travel between the particles. The particles seem to communicate with each other faster than the speed of light, which seems to violate the principle of locality, that objects can only be influenced by their immediate surroundings. B. Bell's theorem and hidden variables. In 1964, John Bell showed that local hidden variable theories, which assume that particles have predetermined hidden properties and interact only locally, cannot reproduce all the predictions of quantum mechanics. Bell derived a mathematical inequality, Bell's inequality, which must hold true for any local hidden variable theory, but which can be violated by quantum mechanics. Bell's theorem essentially says that if quantum mechanics is correct, then the behavior of entangled particles cannot be explained by any local hidden variable theory. Instead, quantum mechanics predicts correlations that cannot be explained by classical local causality. 3. The Bell inequality and experimental tests. A. Bell's inequality provides a testable distinction between quantum mechanics and local hidden variable theories. It shows that under certain conditions, the correlations predicted by quantum mechanics will violate the inequality, whereas local hidden variable theories cannot. This inequality is based on measurements of entangled particles, and it predicts that the correlation between measurements will exceed certain bounds if quantum mechanics is correct. The violation of Bell's inequality implies that local realism, the idea that particles have definite properties and are only influenced by local interactions, cannot explain quantum entanglement. If experimental measurements show that the inequality is violated, it means that non-local effects are at play, meaning that particles can be instantaneously correlated across space. B. Experimental confirmation. In the 1980 AS, Alain Aspect and his team conducted experiments to test Bell's inequality. They used entangled photons and measured their polarizations at different angles. The results of these experiments violated Bell's inequality, providing strong evidence for quantum non-locality. The measurements showed that the entangled particles exhibited correlations that could not be explained by any local hidden variable theory. These experimental results were consistent with the predictions of quantum mechanics and demonstrated that non-locality is a real feature of the quantum world. The experiments effectively confirmed that quantum entanglement cannot be explained by any theory that assumes local hidden variables. 4. The paradox. What does non-locality mean for reality? A. The nature of quantum non-locality. The Bell's theorem paradox forces us to confront the idea that the nature of reality is deeply non-local. In classical physics, we assume that objects are independent and interact in a local manner. However, the results of Bell's theorem and the violation of Bell's inequality suggest that the fundamental nature of particles is interconnected in ways that transcend spatial separation. The behavior of one particle instantaneously affects the behavior of another, even if they are light years apart. This non-local behavior challenges our classical intuitions about causality, separability, and locality. If particles can be instantaneously correlated, then what does this say about space, time, and causal relationships? Does this mean that our understanding of spatial separation and local interactions needs to be fundamentally revised? B. Implications for our understanding of the universe. The violation of locality in quantum mechanics has profound philosophical implications. It suggests that the universe is fundamentally interconnected in ways that are not immediately apparent in classical physics. The non-local correlations observed in entangled particles imply that the universe may be a holistic system, where events in one part of space can instantaneously affect distant parts of the universe. This raises questions about information transfer, causality, and the structure of reality itself. If non-local effects are real, how do we reconcile them with the principles of special relativity, which prohibits faster-than-light communication? Does quantum mechanics suggest a new model of spacetime, where the traditional concepts of locality and separability are not applicable? Double-slit experiment paradox. Imagine you are setting up an experiment where particles, such as electrons or photons, pass through a barrier with two slits, and you measure where they land on a screen behind the barrier. If you weren't measuring which slit the particles went through, they would create an interference pattern, a characteristic wave-like behavior. But the paradox emerges when you observe or measure the particles, aiming to figure out which slit they went through. Instead of the expected wave-like interference pattern, you get two distinct patterns, as if the particles behaved like individual particles rather than waves. This is the double-slit experiment paradox, where the act of observation seems to fundamentally change the outcome of the experiment. How can particles exhibit both wave-like and particle-like behavior depending on whether they are observed, and what does this say about the role of the observer in quantum mechanics? The paradox challenges our classical understanding of reality, suggesting that the very act of observation or measurement might influence the fundamental nature of particles. Let's explore the double-slit experiment paradox, where wave-particle duality and the observer effect collide in a fascinating mystery at the heart of quantum mechanics. The double-slit experiment was first performed by Thomas Young in 1801 to demonstrate the wave nature of light. He passed light through two slits and observed an interference pattern on a screen, indicating that light behaved as a wave. This experiment was one of the first pieces of evidence for the wave theory of light. However, the paradox emerged when the experiment was repeated in the 20th century with individual particles like electrons or photons. When these particles are fired one by one through the slits, they should behave like particles and create two distinct patterns on the screen. But when no one is observing which slit the particle passes through, the particles behave as if they were waves, creating an interference pattern. This behavior suggests that the particle passes through both slits simultaneously, in a state of superposition. The paradox deepens when a detector is placed to measure which slit the particle goes through. In this case, the interference pattern disappears, and the particle behaves like a classical particle, going through one slit or the other. The double-slit experiment paradox challenged the traditional understanding of classical physics and was one of the key experiments that led to the development of quantum mechanics. It revealed the peculiar nature of quantum wave-particle duality, where particles can exhibit both particle-like and wave-like behavior depending on whether they are observed. The paradox also introduced the concept of quantum superposition and raised deep questions about the role of the observer in quantum mechanics. The double-slit experiment paradox is one of the most well-known and puzzling experiments in the history of quantum mechanics. It reveals the wave-particle duality of matter and energy, showing that particles can behave as both waves and particles depending on whether they are observed. The paradox challenges our classical understanding of the nature of reality and the role of the observer in quantum mechanics. 1. The classical experiment. Light as a wave, A. The setup. The original double-slit experiment was performed by Thomas Young in the early 19th century to demonstrate the wave nature of light. In the experiment, light was directed at a barrier with two slits, and the light that passed through the slits was projected onto a screen behind the barrier. Instead of producing two bright spots corresponding to the slits, the light created an interference pattern on the screen, characteristic of wave-like behavior. The interference pattern consists of alternating bright and dark bands, which occur because the waves of light passing through the slits interfere with each other. Where the waves are in phase, they reinforce each other and produce a bright band, while where they are out of phase, they cancel each other out, producing a dark band. B. The wave interpretation. Young's experiment was key in the acceptance of wave theory of light, which competed with the particle theory of light proposed by Isaac Newton. The interference pattern was difficult to explain using the particle theory, but it was easily explained by the wave theory, which described light as a series of oscillating electric and magnetic fields. The classical interpretation of the double-slit experiment suggested that light, as a continuous wave, passed through both slits simultaneously and interfered with itself, creating the observed pattern. This wave-like nature of light seemed well established in the context of classical physics. 2. The quantum version of the double-slit experiment. A. Particles as waves. When the double-slit experiment was repeated with individual particles, such as electrons or photons, in the 20th century something strange occurred. Instead of observing a pattern that would correspond to the behavior of individual particles, i.e. two distinct bands corresponding to the two slits, an interference pattern emerged on the screen, just like the pattern produced by waves. This was surprising because electrons and photons are fundamentally particles, not waves. Even more perplexing, when individual particles, such as electrons, were fired at the slits, each particle seemed to interfere with itself, as though it was passing through both slits at the same time. The particles did not follow a single trajectory, through one slit or the other. They behaved as if they were simultaneously in multiple places. The interference pattern emerged even though the particles were sent through the slits one at a time, leading to the idea that the wave function describing the particle's behavior was spread out, with the particle existing in a superposition of states. B. The role of the observer. The paradox deepens when you place a detector at one of the slits to determine which slit the particle passes through. When this observation is made, the interference pattern disappears, and the particles behave as individual particles, creating two distinct bands on the screen, exactly as classical physics would predict. The act of measurement, or observation, seems to cause the particles to collapse from their wave-like superposition into a definite particle state. This suggests that the act of observing or measuring the particles somehow influences their behavior, causing them to behave like particles rather than waves. The paradox lies in the fact that the particles seem to choose a behavior, wave or particle, depending on whether they are observed. This leads to the question: does the observer play a fundamental role in determining the outcome of quantum events? 3. The paradox, wave-particle duality and quantum superposition. A. Wave-particle duality. The double-slit experiment. Paradox is a manifestation of the wave-particle duality of quantum mechanics. The idea that particles like electrons and photons can exhibit both wave-like and particle-like behavior. This duality challenges the classical understanding that objects can only behave as waves or particles. Instead, quantum mechanics suggests that the nature of the particle depends on the type of measurement performed. When unmeasured, the particle exhibits wave-like interference. However, when the particle is measured, it behaves like a classical particle, with a definite position and trajectory. This duality is at the core of quantum mechanics and highlights the indeterminacy inherent in the quantum world. B. Quantum superposition. The concept of quantum superposition is key to understanding the double-slit experiment paradox. In quantum mechanics, particles do not exist in a single definite state until they are measured. Instead, they exist in a superposition of all possible states. In the case of the double-slit experiment, the particle is in a superposition of going through both slits at the same time, leading to interference. It is only when the particle is measured that the superposition collapses and the particle chooses a definite state, either passing through one slit or the other. The paradox arises because, in the absence of measurement, quantum particles behave like waves, interfering with themselves. But as soon as a measurement is made, the particle behaves like a classical particle, exhibiting definite properties. This introduces the question: what determines the outcome of the measurement, and how does the observer affect the quantum system? 4. The role of the observer in quantum mechanics. A. The observer effect. The double-slit experiment paradox is intrinsically linked to the observer effect, the idea that the act of observation or measurement affects the system being observed. In quantum mechanics, this effect is particularly pronounced because wave function collapse occurs when the system is measured. The wave function, which describes the probabilities of all possible outcomes, collapses into a single definite state when the system is observed. This collapse is not governed by any classical mechanics, but by the probabilistic nature of quantum mechanics. The paradoxical behavior of the particle, acting as a wave when unobserved and as a particle when measured, raises deep questions about the role of consciousness and observation in quantum mechanics. Does the observer's interaction with the system cause the wave function to collapse, or is the collapse an intrinsic feature of the system itself? B. The many-worlds interpretation. One potential resolution to the double-slit experiment paradox comes from the many-worlds interpretation, MWI, of quantum mechanics. According to MWI, every possible outcome of a quantum measurement actually occurs, but in separate, non-interacting branches of the universe. In this interpretation, when a particle is measured, the universe splits into multiple realities, each corresponding to a different outcome of the measurement. This means that the particle is both a wave and a particle, but each possibility exists in a different branch of reality. The many-worlds interpretation provides an elegant solution to the paradox, where the wave function doesn't collapse. Instead, all outcomes occur, but in different parallel worlds. While this interpretation avoids the need for a wave function collapse, it also leads to the strange idea that the universe is constantly splitting into multiple realities. 5. Real-world implications and quantum technologies. A. Quantum interference and computing. The double-slit experiment paradox has profound implications for the development of quantum technologies, particularly quantum computing. In quantum computing, the superposition of quantum states is used to perform computations far more efficiently than classical computers. The behavior of quantum particles, which can exist in multiple states simultaneously, allows quantum computers to perform parallel calculations. Quantum interference, demonstrated in the double-slit experiment, is a fundamental resource for quantum computers. By exploiting the wave-like nature of quantum particles, quantum computers can process information in ways that classical computers cannot. B. Quantum cryptography. Quantum key distribution relies on the Heisenberg uncertainty principle, where the act of observing a quantum system affects its state. This ensures that any eavesdropping on a quantum communication system will be detectable, as the act of observation alters the transmission, thus providing unbreakable encryption. EPR paradox. Imagine two particles created in the same interaction moving in opposite directions. You measure one particle's properties and immediately you know the properties of the second, regardless of how far apart the particles are. This phenomenon is called quantum entanglement, and it suggests that particles can be instantaneously correlated with one another, even across vast distances. But here's the paradox. If these particles are separated by space, how can they communicate with each other faster than light, seemingly defying the principle of locality and the speed of light limit set by special relativity? This problem was raised in the EPR paradox, formulated by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935. The EPR paper argued that quantum mechanics, as it was understood, must be incomplete, because it implied that information could travel faster than the speed of light, violating the principles of locality and causality. The EPR paradox challenges our understanding of reality, suggesting that quantum mechanics may require a deeper theory, one that is non-local and potentially hidden from view. Let's dive into the EPR paradox, where entanglement, non-locality, and the nature of quantum reality collide in a challenge to both classical physics and special relativity. The EPR paradox was introduced in 1935 by Albert Einstein, Boris Podolsky, and Nathan Rosen in a seminal paper that sought to critique the completeness of quantum mechanics. The paper, titled "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?", presented a thought experiment involving quantum entanglement, a phenomenon where two particles are created in such a way that their properties are correlated, no matter how far apart they are. Einstein, Podolsky, and Rosen, EPR, argued that quantum mechanics must be incomplete because it suggested that measuring one particle could instantaneously affect the state of the other particle, even if the particles were separated by vast distances, a phenomenon they found troubling. They reasoned that if quantum mechanics were complete, it would violate the principle of locality, the idea that objects can only be influenced by their immediate surroundings, and the speed of light limit set by special relativity. In their view, quantum mechanics could not provide a full description of physical reality because it allowed for this spooky action at a distance, a term famously coined by Einstein. The EPR paper set the stage for deep philosophical and scientific debates about the nature of quantum entanglement and locality. While Einstein hoped that his arguments would reveal flaws in quantum mechanics, the paradox sparked more work on quantum non-locality and laid the foundation for future experiments on the phenomenon of entanglement. The Bell's theorem and subsequent experiments confirmed that quantum mechanics does indeed predict non-local behavior, leaving us to reconsider the nature of reality and information in the quantum world. The EPR paradox is a thought experiment that raises fundamental questions about the nature of quantum mechanics, particularly in terms of the concepts of locality, causality, and the nature of physical reality. The paradox is centered on the phenomenon of quantum entanglement, where two particles that interact can become correlated in such a way that their properties are instantaneously linked, no matter how far apart the particles are. This apparent instantaneous communication between particles across space raised questions for Einstein, who viewed this as a sign of incompleteness in quantum mechanics. Let's explore the core concepts of the EPR paradox: quantum entanglement, locality, hidden variables, and the completeness of quantum mechanics. We will also discuss how the paradox led to subsequent developments in quantum theory and experimental tests that would ultimately confirm the non-local nature of quantum entanglement. 1. Quantum entanglement, the basis of the paradox. A. The concept of entanglement. Quantum entanglement is one of the most puzzling and fundamental phenomena in quantum mechanics. It occurs when two or more particles become correlated in such a way that their quantum states cannot be described independently of each other, even when the particles are separated by vast distances. For example, if two particles are entangled in terms of their spin, the measurement of one particle's spin will immediately determine the spin of the other particle, regardless of how far apart the particles are. This non-local connection appears to violate the classical idea that physical processes should only be influenced by their immediate surroundings. Entangled particles behave as if they are part of a single quantum system, and their properties, such as spin, polarization, or position, are not determined until measurement. Before measurement, the particles exist in a superposition of all possible states. B. The EPR thought experiment. In the EPR thought experiment, Einstein, Podolsky, and Rosen considered two entangled particles, A and B, that are created in such a way that their quantum states are correlated. The particles are then separated by a large distance, and measurements are made on particle A. According to quantum mechanics, the measurement on particle A instantaneously determines the properties of particle B, even if particle B is far away. Einstein, Podolsky, and Rosen argued that this instantaneous connection between the particles was problematic. They believed that the only way to explain this phenomenon without violating locality and the principle of relativity was to invoke hidden variables, undiscovered factors that could explain the correlation without requiring instantaneous communication between distant particles. The EPR argument was that quantum mechanics must be incomplete because it predicted that particles could be instantaneously correlated over vast distances, violating local realism. The idea that physical properties of objects exist independently of observation and that objects are only influenced by local causes. 2. Locality and causality in the EPR paradox. A. Local realism. The principle of local realism combines two key ideas. Locality, the idea that objects can only be influenced by their immediate surroundings, meaning that interactions between objects must happen through a local process or through signals that propagate at or below the speed of light. Realism, the idea that physical properties of objects, such as position, momentum, or spin, exist independently of observation and are determined before they are measured. In classical physics, local realism is a cornerstone, meaning that if you measure a property of one particle, the state of another particle can only be influenced by direct, local interactions. B. The violation of locality. The EPR paradox forces us to reconsider locality in quantum mechanics. If particles can become entangled and exhibit instantaneous correlations over vast distances, it suggests that non-local interactions may exist. According to quantum mechanics, these correlations are not mediated by any classical signal traveling at the speed of light. Instead, the entangled particles are linked in such a way that the state of one particle affects the state of the other instantaneously, no matter the separation distance. For Einstein, this instantaneous action violated the principle of locality and suggested that quantum mechanics could not provide a complete description of physical reality. He famously referred to this phenomenon as spooky action at a distance. and he believed that a deeper, more complete theory was needed to explain the behavior of entangled particles. 3. Hidden variables. The search for a local theory A. The idea of hidden variables. In their paper, Einstein, Podolsky and Rosen proposed that quantum mechanics might be incomplete and that the correlations between entangled particles could be explained by hidden variables, unobservable parameters that determine the properties of the particles but are not accounted for in the standard quantum mechanical framework. Hidden variable theories aim to provide a local and deterministic explanation for quantum phenomena. In a hidden variable theory, the properties of particles would be predetermined by these variables, and measurement would simply reveal the underlying values. This would restore determinism and locality to the theory, in contrast to the probabilistic and non-local predictions of quantum mechanics. B. Bell's theorem. The experimental challenge John Bell's theorem, formulated in 1964, showed that local hidden variable theories cannot account for the predictions of quantum mechanics. Bell derived a mathematical inequality, Bell's inequality, which must be satisfied by any local hidden variable theory. However, quantum mechanics predicts that this inequality will be violated in entangled particle experiments. In other words, if the predictions of quantum mechanics are correct, they cannot be explained by any local hidden variable theory. Bell's theorem laid the foundation for experimental tests of the EPR paradox. These tests involve measuring the correlations between entangled particles and determining whether they violate Bell's inequality. If the inequality is violated, it would confirm that non-locality is a real feature of quantum mechanics, and hidden variable theories cannot provide a complete description of the system. 4. The experimental confirmation. Quantum non-locality. A. The aspect experiment in the 1980s, Allais Aspect and his team conducted a series of experiments to test Bell's inequality using entangled photons. The results showed that the correlations between the photons violated Bell's inequality, providing experimental evidence for quantum non-locality. These experiments confirmed that quantum mechanics, and not local hidden variable theories, correctly describes the behavior of entangled particles. B. Non-locality in the quantum world. The violation of Bell's inequality in these experiments confirmed that the EPR paradox was not merely a theoretical problem, but a real feature of the quantum world. The instantaneous correlation between entangled particles, regardless of the distance between them, suggests that quantum mechanics predicts a non-local reality, a reality where information can travel faster than the speed of light, violating classical notions of locality and causality. 5. The paradox. What does this say about reality? A. The nature of quantum reality. The EPR paradox raises profound questions about the nature of reality. If quantum particles can be instantaneously correlated across vast distances, it suggests that information in the quantum world is not confined by the limitations of space and time. This non-local behavior challenges our classical understanding of separability and independence in physical systems. What does this mean for the nature of the universe? Is reality fundamentally interconnected, with instantaneous connections between distant parts of the universe? Does this suggest that classical locality is an illusion, and that quantum mechanics is the true description of reality? B. The role of the observer. The EPR paradox also touches on the role of the observer in quantum mechanics. In quantum theory, particles exist in a superposition of states until measured, and the act of measurement collapses the wave function into a definite state. This introduces questions about the observer's role in determining the outcomes of quantum experiments. Does the act of measurement play a fundamental role in the nature of reality itself? Or is there a deeper, more hidden layer of reality that quantum mechanics has not yet uncovered? Extinction paradox. Imagine a species of animals, perfectly adapted to their environment, thriving for generations. They evolve, they grow, and they dominate their ecological niche. But here's the paradox. Why, after millions of years of success, do so many species eventually go extinct? What forces or events could possibly lead to their downfall? The extinction paradox arises from the tension between the seeming perfection of evolutionary adaptation and the inevitable extinction that some species face, despite their seemingly ideal fit in their environment. This paradox challenges the idea that evolution, driven by natural selection, is always a process that leads to better survival strategies. Instead, it reveals a more fragile reality, one where even well-adapted species may face unexpected vulnerabilities. How can a species that has evolved over time to be so perfectly adapted to its environment become extinct? And why do so many species, despite their remarkable adaptations and survival mechanisms, eventually disappear? Let's dive into the extinction paradox, where evolution, adaptation, and the balance of life collide in an unsettling and thought-provoking challenge to our understanding of survival and the nature of existence. The extinction paradox is a long-standing question in the study of evolutionary biology, stemming from the work of Charles Darwin and later theory of natural selection. Darwin's theory proposed that organisms evolve through natural selection, with mutations that provide a survival advantage passed down through generations. The process seems straightforward. Species adapt to their environment, and the fittest survive. However, the paradox arises when we observe the long-term patterns of life on Earth. Despite the intricate processes of evolution, many species that once thrived become extinct, often without clear explanation. Extinctions are part of the natural evolutionary process, but they pose a paradox. How can highly specialized, well-adapted species vanish despite their evolutionary success? Throughout history, the study of mass extinctions, such as the Permian-Triassic extinction or Cretaceous-Paleogene extinction, has revealed that large-scale disruptions to ecosystems can devastate even the most well-adapted species. The extinction paradox also extends to more gradual extinctions, where species fade over time due to ecological shifts, competition, or climate changes, raising questions about the fragility of evolutionary success. The extinction paradox forces us to reconsider our understanding of evolutionary theory. Despite the power of natural selection, why does it not always lead to a species' continued survival? Is it simply that extinction is an inevitable part of the evolutionary process? Or is there something more fundamental at play? The extinction paradox lies at the intersection of evolution, survival, and the unpredictable forces that drive the rise and fall of species. At its core, the paradox arises from the observation that species can become extinct despite having evolved through natural selection to become perfectly adapted to their environment. This apparent contradiction challenges our understanding of survival and adaptation, suggesting that evolutionary success does not always guarantee long-term survival. 1. Evolution and adaptation. The basis of survival. A. Natural selection and adaptation. In evolutionary biology, natural selection is the process by which species evolve traits that increase their chances of survival and reproduction in a particular environment. Survival of the fittest means that individuals with traits that give them a reproductive advantage are more likely to pass those traits on to their offspring. Over many generations, these beneficial traits become more prevalent in the population, leading to adaptation. Adaptation is a continuous process driven by environmental pressures, such as food availability, climate, predators, and competitors. For example, camouflage, sharp claws, or speed might evolve in response to the need to avoid predators, while sharp teeth or better foraging strategies might evolve to improve a species' ability to gather food. B. The illusion of perfection. Despite the apparent perfection of an organism's adaptations, the concept of absolute perfection in evolution is misleading. Species may become exceptionally well suited to their environment, but this does not ensure long-term survival. Evolution is always occurring in a changing environment, where new threats, shifting resources, and climate changes create challenges that well-adapted species may not be able to overcome. This creates the paradox. Even highly specialized species can be vulnerable to unpredictable factors, despite their adaptation to their environment. 2. The fragility of evolutionary success. A. The dynamic nature of ecosystems. Ecosystems are not static. They are constantly shifting due to environmental changes, such as climate change, volcanic eruptions, or meteorite impacts. A species that is perfectly adapted to its environment at one point in time may find that the environmental conditions change, making its adaptations less beneficial or even detrimental. The extinction paradox reveals that even well-adapted species may become vulnerable if their environment shifts in unpredictable ways. For example, a species that evolves to thrive in a tropical climate might struggle if the climate changes and becomes cooler or drier. The species' specialized traits, though once advantageous, become liabilities as the environment changes. The role of mass extinctions throughout Earth's history. There have been several mass extinction events where large numbers of species went extinct in a short period. These extinctions were often caused by large-scale disruptions, such as asteroid impacts, volcanic activity, or climate shifts. In many cases, species that were highly adapted to specific environments were wiped out, even though they were perfectly suited to their niche. For example, the Cretaceous-Paleogene extinction event, which caused the extinction of the dinosaurs, was likely triggered by an asteroid impact that dramatically changed the Earth's climate. Despite the dinosaurs being the dominant life forms on Earth for millions of years, they could not survive the sudden and dramatic changes brought on by this event. The dinosaurs' adaptations to their environment were insufficient to cope with the rapid global changes that followed. The extinction paradox emphasizes that adaptation and evolutionary success do not guarantee a species' long-term survival if it is suddenly confronted with a large-scale disruption. 3. Gradual extinctions and the role of competition. A. The slow fade of species. Not all extinctions occur suddenly. In many cases, species gradually fade away over time due to competition from other species, environmental changes, or the decline in reproductive success. The extinction paradox is also seen in these gradual extinctions, where species with well-developed adaptations may slowly lose out to other species that are better suited to new conditions. For instance, in an ecosystem where resources are limited, species that are highly specialized may be outcompeted by more generalist species that can survive in a wider range of conditions. As the specialized species struggle to find food, their populations decrease, and they may eventually go extinct, despite being well adapted to a specific niche. B. The impact of environmental shifts, changes in the climate or habitat, can also lead to gradual extinctions. For example, a species that evolved to live in a wetland might thrive in that environment for generations, but as the wetland dries up or is replaced by a forest, the species may not be able to adapt quickly enough to the changing conditions. The environmental shift causes the species to become less well suited to its habitat, leading to a slow decline and eventual extinction. 4. The evolutionary arms race, adaptation and vulnerability. A. The cost of specialization. The paradox of extinction also arises from the cost of specialization. Highly adapted species may face an evolutionary trade-off. Their specific traits, which provide them with a survival advantage in certain conditions, may leave them vulnerable when conditions change. Specialization can make species incredibly successful in one area, but it also makes them less flexible in the face of change. For example, certain species of birds or insects may evolve highly specialized feeding habits or habitats, but when resources become scarce or competitors emerge with more generalized survival strategies, these species may find themselves at a disadvantage. Their evolutionary success becomes a vulnerability when the environment or competition changes. B. Evolutionary trade-offs and extinction. The extinction paradox suggests that evolution is not a linear path toward constant improvement. Instead, it involves a series of trade-offs. Specialization can lead to greater survival in stable environments, but it also makes species vulnerable to change. The more specialized a species becomes, the more it risks extinction when the very conditions it has adapted to change. 5. The unpredictability of extinction. A. Evolution and the role of randomness. One of the key features of the extinction paradox is the unpredictability of extinction. While evolutionary theory provides a framework for understanding how species adapt to their environments, it cannot predict exactly when or why a species will go extinct. Evolutionary is a process that is subject to random mutations, environmental factors, and chance events. Mass extinction events, gradual environmental changes, or even small, seemingly insignificant changes in an ecosystem can have profound effects on species. As a result, extinction remains a fundamentally unpredictable process, despite the overall trend of evolution toward adaptation and survival. B. The inevitable fate of all species, the extinction paradox, also reminds us that extinction is an inevitable part of the evolutionary process. Even species that have been perfectly adapted to their environments for millions of years eventually face extinction. Whether through competition, environmental change, or a catastrophic event, all species are ultimately subject to the forces of evolution and natural selection. This inevitability of extinction highlights the fragility of life on Earth and the unpredictable nature of the forces that drive evolution. Hardy's paradox. Imagine you are observing a quantum system, and a measurement is made on a quantum particle, such as an electron. The measurement outcome is predicted by the quantum wave function. But here's the twist. The prediction does not always match what we would expect based on classical intuition. Hardy's paradox, introduced by Lucian Hardy in 1992, explores a situation where quantum mechanics seems to violate classical expectations of how systems should behave. In this paradox, we encounter a quantum superposition of events that leads to a non-classical correlation that defies our usual understanding of measurement and reality. Hardy's paradox suggests that non-locality and entanglement are not just theoretical concepts, but can produce observable effects in specific quantum systems. How can quantum systems exhibit counterintuitive behavior that goes beyond the standard predictions of classical physics? Hardy's paradox forces us to confront the nature of measurement, quantum superposition, and the role of entanglement in a way that challenges the very foundation of quantum mechanics. Let's explore Hardy's paradox, where quantum theory and measurement theory collide in a stunning example of non-classical behavior. Hardy's paradox was proposed by Lucian Hardy in 1992 as a thought experiment to explore the foundations of quantum mechanics. Hardy's work came in the context of a broader investigation into the interpretation of quantum mechanics, specifically the measurement problem and the role of quantum superposition. Hardy's paradox is a variation on quantum entanglement and non-locality, which suggests that quantum systems can exhibit correlations that classical systems cannot. The paradox arises from a scenario in which particles are entangled and placed in a superposition of states. Hardy's paradox specifically involves a quantum system that seems to produce results which should not be possible according to classical local realism. The central issue of the paradox is that quantum systems can produce non-local correlations even when the particles are spatially separated, and the outcomes of measurements on these particles cannot be predicted by any local hidden variable theory. The paradox challenged previous assumptions and reinforced the idea that quantum systems defy classical intuition, particularly when it comes to measurement and entanglement. Hardy's paradox built on previous work in quantum mechanics, such as Bell's theorem and the EPR paradox, by highlighting that certain quantum experiments could produce results that are seemingly impossible according to classical physics. These non-local correlations play a crucial role in quantum phenomena and have profound implications for how we understand the measurement problem and the nature of reality. Hardy's paradox is a thought experiment designed to illustrate the strange and counterintuitive nature of quantum mechanics, specifically the nature of quantum measurement and entanglement. It explores a situation in which quantum systems can produce non-local correlations that classical physics simply cannot explain. The paradox emphasizes the fact that quantum systems do not follow the rules of local realism, the idea that objects have definite properties and can only be influenced by their immediate surroundings. 1. Background. The measurement problem in quantum mechanics. A. The measurement problem. One of the central issues in quantum mechanics is the measurement problem. The question of how and why quantum systems appear to behave as waves until they are measured. The wave function, which describes the quantum state of a system, evolves according to the Schrödinger equation. But when a measurement is made, the wave function collapses and the system adopts a definite state. The measurement problem asks, what causes this collapse, and why do quantum systems behave probabilistically until observed? In classical mechanics, the state of a system is always well-defined and deterministic. However, quantum mechanics introduces uncertainty at the fundamental level. The Heisenberg uncertainty principle suggests that we cannot simultaneously know both the position and momentum of a particle with perfect accuracy. This creates a fundamental indeterminacy that governs the behavior of all quantum systems. The paradox arises when quantum systems, particularly entangled systems, behave in ways that defy classical expectations. The wave function collapse and the probabilistic nature of quantum mechanics seem to suggest that the act of measurement plays a crucial role in determining the state of a system. B. Superposition and quantum entanglement. Quantum superposition is another key concept in quantum mechanics. It refers to the phenomenon where a quantum system can exist in a superposition of states, meaning it can be in multiple states simultaneously. For example, a particle can be in a superposition of being both spin up and spin down until it is measured. Quantum entanglement occurs when two particles are created in such a way that their states are correlated, These particles can be separated by vast distances, but their quantum states remain linked. When a measurement is made on one particle, the state of the other particle is instantaneously determined, regardless of the distance between them. This phenomenon seems to violate local realism, the idea that objects are only influenced by their immediate surroundings. The EPR paradox and Bell's theorem showed that quantum mechanics cannot be explained by local hidden variable theories, and that quantum entanglement leads to non-local correlations that defy classical explanations. Hardy's paradox builds on this idea, illustrating how quantum mechanics can produce results that classical physics cannot explain. 2. Hardy's paradox, the thought experiment, A. The setup. Hardy's paradox involves an entangled quantum system with multiple possible outcomes. The system consists of two particles, say A and B, that are entangled. Both particles are sent through a series of measurements with the following conditions. The particles are measured for certain properties, such as polarization or spin. The measurements are performed in such a way that the system is in a superposition of possible states, but the final outcome of the system cannot be determined in advance. The paradox arises from the fact that the outcome of measurements can produce correlations that are impossible to explain using classical physics. When the measurements are combined, the results suggest that the particles are exhibiting non-local correlations. They are instantaneously linked in a way that cannot be explained by classical physics or any local hidden variable theory. B. The non-local correlations in Hardy's paradox. The non-local correlations are evident when we look at the combined results of the measurements. Even though the particles are measured separately, the results indicate that the particles are behaving as if they are in a non-local superposition, a state in which their properties are not determined until they are measured. For example, if particle A is measured in one basis, say spin up or spin down, and particle B is measured in a different basis, such as horizontal or vertical polarization, the outcome of one measurement can influence the outcome of the other. This happens instantaneously, regardless of the distance between the particles. The paradox lies in the fact that these instantaneous correlations seem to defy the locality principle and suggest that the particles are somehow communicating with each other faster than the speed of light. C. The apparent violation of local realism. The key feature of Hardy's paradox is that it violates classical assumptions of local realism. In classical physics, the outcome of a measurement should depend only on the local conditions of the system and should not be influenced by distant, entangled particles. However, the paradox shows that quantum mechanics allows particles to be instantaneously correlated across space, with no direct interaction between the two. Hardy's paradox suggests that local realism cannot fully explain the behavior of entangled quantum systems. Instead, quantum mechanics relies on the idea that the wave function describing the system is non-local. The properties of the system are not determined until the wave function collapses upon measurement. 3. Implications for quantum theory and the nature of reality. A. Quantum non-locality. The primary implication of Hardy's paradox is that quantum mechanics is inherently non-local. It challenges the classical notion that objects only interact with their immediate surrounding. Instead, quantum particles can be instantaneously correlated, even when separated by vast distances. This suggests that quantum mechanics involves a deeply interconnected reality, where information can travel between particles in a way that is not constrained by the speed of light. This non-locality raises questions about the nature of space and causality in the quantum world. If particles can be entangled and instantaneously influence each other, does this mean that the classical concepts of locality and causality are no longer valid at the quantum level? What does this mean for our understanding of time and information? B. The role of measurement. Hardy's paradox also highlights the role of measurement in quantum mechanics. In classical physics, the state of a system is always well defined, and measurements simply reveal properties that already exist. However, in quantum mechanics, the act of measurement affects the system and determines the outcome. The wave function collapse is a crucial concept here. The measurement of one particle's properties determines the state of the other particle, even if they are far apart. This suggests that observation or measurement is not just a passive act of gathering information. Instead, it plays an active role in shaping the reality of the system being measured. 4. Experimental confirmation and future research. A. Quantum interference and Bell's inequality. While Hardy's paradox was initially a thought experiment, it is closely related to the experimental tests of quantum non-locality, such as Bell's theorem and the Bell inequality. Experiments measuring the correlations between entangled particles have consistently violated Bell's inequality, providing experimental evidence for the non-local nature of quantum mechanics. These experiments support the idea that quantum systems exhibit non-local correlations that cannot be explained by local hidden variable theories. Hardy's paradox helps to solidify the understanding that quantum mechanics predicts a non-local reality, one that does not adhere to classical notions of separability and independence. B. Quantum computing and quantum communication. The insights from Hardy's paradox and the broader study of quantum non-locality have important implications for quantum technologies. Quantum computing and quantum cryptography rely on the entanglement and non-local correlations that Hardy's paradox illustrates. By exploiting the wave-particle duality and quantum superposition, quantum computers can perform tasks much faster than classical computers. In quantum communication, the principles of entanglement and non-locality can be used to create unbreakable encryption and secure communication channels, as any attempt to measure the quantum state of the system would alter the system and reveal the eavesdropping. Klein paradox. Imagine a particle, like an electron, moving toward a potential barrier that would ordinarily block its path. In classical physics, this would mean that the particle simply cannot pass the barrier. But in the strange world of quantum mechanics, things are different. Thanks to a phenomenon called quantum tunneling, the particle can sometimes pass through barriers that, according to classical theory, it should not be able to surmount. But here's the paradox. When this concept is applied to relativistic particles, like electrons traveling near the speed of light, the behavior becomes even more puzzling. The Klein paradox, first formulated by Oscar Klein in 1929, arises when we consider relativistic quantum particles encountering potential barriers. In this paradox, relativistic particles, such as electrons, can actually be reflected by a potential barrier, but under certain conditions, they can also be transmitted with negative energy. This goes against our classical understanding of energy and stability in physical systems. The Klein paradox raises fundamental questions about how relativity and quantum mechanics intersect, and why relativistic particles behave so differently from what we would expect. Let's explore the Klein paradox, where quantum tunneling, relativity, and particle behavior converge in a surprising and counterintuitive result that challenges our view of energy and stability in the quantum world. The Klein paradox was formulated by Oscar Klein in 1929 as part of his work on the Dirac equation, which describes the behavior of relativistic quantum particles, such as electrons. The Dirac equation is an important advancement in quantum mechanics because it combines the principles of quantum mechanics with special relativity, providing a framework for understanding particles moving at speeds close to the speed of light. The Klein-Gordon equation is an extension of the Dirac equation for scalar fields, and it predicts the behavior of relativistic particles encountering potential barriers. In the Klein paradox, Klein applied the Dirac equation to a particle that encounters a potential barrier and discovered something unexpected. When the barrier is very strong, the particle is not only reflected as expected, but can also be transmitted with negative energy. This result contradicted classical intuition, which dictates that particles should never have negative energy. Klein's work laid the foundation for understanding the behavior of relativistic particles in the context of quantum mechanics. The paradox remains significant in quantum field theory as it raises important questions about the nature of particles and the role of energy in quantum systems. Over the years, the Klein paradox has contributed to the understanding of quantum tunneling and the nature of relativistic particles, particularly in the context of phenomena like electron-positron pair production and high-energy physics experiments. The Klein paradox reveals a deep connection between quantum mechanics and special relativity, particularly when it comes to understanding the behavior of particles at high velocities. The paradox involves relativistic particles, like electrons moving near the speed of light, encountering a potential barrier and behaving in a way that defies classical physics. The paradox is centered around the Dirac equation, which describes relativistic particles, and its predictions for how such particles interact with potential barriers. 1. The Dirac equation and relativistic particles. A. The Dirac equation. The Dirac equation, formulated by Paul Dirac in 1928, was a monumental development in quantum mechanics. It combines the principles of quantum mechanics with special relativity, providing a relativistic wave equation for particles like electrons. Unlike the non-relativistic Schrödinger equation, the Dirac equation accounts for the fact that particles can travel at speeds close to the speed of light, which is essential for understanding the behavior of high-energy particles. The Dirac equation is written as x is plus mc2 equals E, where and R matrices. P is the momentum operator, m is the mass of the particle, c is the speed of light, E is the energy of the particle, and is the wave function of the particle. The Dirac equation describes the behavior of spin 1/2 particles, such as electrons, and incorporates the concept of spin into a relativistic framework. It also predicts the existence of antimatter, particles like positrons, which have the same mass as electrons but opposite charge. B. Relativistic quantum mechanics. In the context of relativistic quantum mechanics, the Dirac equation predicts that electrons can have both positive and negative energies. This is a key feature of relativistic particles, and it leads to several paradoxical results. The idea that particles can have negative energy was troubling for early physicists, as it seemed to violate the classical understanding of energy. The concept of negative energy is at the heart of the Klein paradox. While classical physics does not allow negative energy states, relativistic quantum mechanics predicts that certain systems, especially when interacting with strong fields or potential barriers, can exhibit negative energy solutions. 2. The Klein paradox, the setup, a potential barrier, and the Dirac equation. In Hardy's thought experiment, a relativistic particle, such as an electron, is sent toward a potential barrier. In the context of the Dirac equation, the potential is typically represented by a scalar potential, Vxx, which varies with position and can represent an energy barrier. When a relativistic particle approaches a potential barrier, classical intuition tells us that the particle should either be reflected or transmit through the barrier. For particles with energy lower than the barrier, classical mechanics would predict reflection. For particles with energy higher than the barrier, classical mechanics predicts transmission. B. The paradox. Negative energy transmission. However, in the Klein paradox, the relativistic particle behaves very differently from what is expected in classical physics. When a particle encounters a highly strong potential barrier, it can be transmitted through the barrier, even if its energy is lower than the barrier. Moreover, the particle can also transmit with negative energy, which seems to violate our conventional understanding of energy stability. This result is based on the solutions to the Dirac equation for relativistic particles interacting with a potential. These solutions suggest that under certain conditions the particles can be transmitted with negative energy, which is physically problematic because negative energy would imply that the particle's energy is lower than its rest mass energy, leading to a violation of stability. C. Quantum tunneling and the Klein paradox. The Klein paradox is related to the phenomenon of quantum tunneling, where particles have a non-Venn probability of passing through barriers, even when their energy is below the height of the barrier. In classical physics, a particle with insufficient energy cannot pass through the barrier. However, in quantum mechanics, the wave function associated with the particle can extend into the classically forbidden region, allowing the particle to tunnel through the barrier. In the case of the Klein paradox, relativistic particles exhibit a form of tunneling, where they not only pass through the barrier, but do so with negative energy. This outcome is a direct consequence of the relativistic nature of the particle and the non-classical solutions to the Dirac equation. 3. The role of negative energy, A. The meaning of negative energy. The concept of negative energy is central to understanding the Klein paradox. In classical mechanics, energy is always positive or zero, as energy represents the ability of a system to perform work. However, in the relativistic quantum framework, the Dirac equation allows for solutions that predict negative energy states. The paradox arises when a relativistic particle encountering a potential barrier transmits with negative energy. In classical mechanics, this would be impossible because energy cannot be less than zero. But in relativistic quantum mechanics, the solutions to the Dirac equation allow for this possibility, challenging our classical notions of stability and energy. B. The consequences of negative energy. In the Klein paradox, The transmission of particles with negative energy suggests that particles can decay into these negative energy states, leading to a cascade of energy loss. This is problematic because it implies that particles could spontaneously decay into lower energy states, leading to instability in the system. This idea was so counterintuitive that it led to further developments in the understanding of quantum field theory and the concept of vacuum fluctuations. 4. Resolution and implications for quantum field theory. A. The Dirac sea and vacuum fluctuations. One of the most profound implications of the Klein paradox is its relationship to the concept of the Dirac sea, a theoretical model proposed by Paul Dirac to explain the existence of positrons, the antimatter counterpart of electrons. According to this model, the vacuum is not empty, but filled with a sea of negative energy states. In this model, electrons occupy the positive energy states, while the negative energy states are filled. When a relativistic electron interacts with a potential barrier, it can be understood as exciting a positron from the Dirac sea, leading to a pair creation event where the electron is transmitted with negative energy. This process can be interpreted as the electron's negative energy state being filled by a positron, leading to the appearance of electron-positron pairs. B. Quantum field theory and particle creation. The Klein paradox also foreshadows the understanding of quantum field theory, where particles are seen as excitations in underlying quantum fields. In this framework, vacuum fluctuations can lead to the creation of virtual particles, which can temporarily violate energy conservation but are constrained by the uncertainty principle. The pair production seen in the Klein paradox is an early example of such phenomena, where high-energy interactions can lead to the creation of particles with negative energy. See modern interpretations and high-energy physics. In modern quantum field theory, the Klein paradox is understood as part of the broader framework of quantum tunneling, particle creation, and energy fluctuations. It helps to explain phenomena like electron-positron pair production and the behavior of high-energy particles in strong fields. It also plays a role in understanding how relativistic quantum systems behave under extreme conditions, such as those encountered in particle accelerators and astrophysical phenomena. Mott paradox. Imagine an electron traveling through a region of space where a nucleus is positioned. According to classical physics, the electron should experience a certain deflection or scattering as it interacts with the electromagnetic field of the nucleus. However, in the Mott paradox, this simple scenario takes an unexpected turn. The paradox occurs when, instead of simply scattering, the electron-positron pairs are created. This seems to violate classical expectations, where the interaction between an electron and a nucleus should not produce such particle-antiparticle pairs. In the Mott paradox, the process of scattering involves the creation of virtual particles or pair production, a concept typically associated with high-energy physics. How can an electron at relatively low energies lead to the creation of electron-positron pairs? This paradox challenges our understanding of quantum scattering, field theory, and the limits of particle creation in quantum mechanics. Let's explore the Mott paradox, where quantum effects, scattering, and pair production combine in a surprising twist that defies classical expectations. The Mott paradox was introduced by Niels Mott in the early 1930s, as part of his work on quantum scattering and the interaction between particles and electromagnetic fields. The paradox arises when an electron undergoes scattering in the presence of a nucleus, and the interaction leads to the creation of electron-positron pairs, a process typically associated with high-energy collisions rather than with lower-energy scattering events. Mott's work in quantum mechanics and field theory aimed to describe how particles behave when interacting with other particles, particularly in situations where the forces involved are governed by the electromagnetic field. In classical physics, the scattering of electrons by nuclei is a well-understood process where electrons are deflected due to their interaction with the nuclear charge. However, the Mott paradox shows that when quantum mechanics is taken into account, the behavior of the electron becomes much more complicated. The Mott paradox was an early example of how quantum field theory could produce unexpected outcomes, such as the spontaneous creation of particles. It contributed to the development of the modern understanding of quantum electrodynamics, QED, which describes the interactions between electrons, photons, and positrons. Mott's work also helped set the stage for further research into pair production and virtual particles, concepts that would become crucial to high-energy physics and the understanding of quantum fields. The Mott paradox is a fascinating phenomenon in the realm of quantum mechanics, particularly in quantum field theory, where scattering processes involve unexpected particle creation. At its core, the paradox is concerned with electron scattering, a process where an electron interacts with a nucleus and is deflected, but instead of merely scattering, the electron can, under certain conditions, create an electron-positron pair. This behavior seems to contradict our classical understanding of scattering processes, and is an example of how quantum effects can produce results that are difficult to explain using classical physics alone. 1. Classical scattering, the basics of electron-nucleus interaction A. The Coulomb interaction. In classical physics, the scattering of an electron by a nucleus is described by the Coulomb force, which is the electrostatic force between the electron, a negatively charged particle, and the nucleus, which carries a positive charge. The strength of the Coulomb interaction depends on the distance between the two particles and the charge of the nucleus. For an electron scattering from a nucleus, the interaction typically leads to the electron being deflected from its path. The amount of deflection depends on the energy of the electron and the nuclear charge. This classical picture works well for low-energy interactions, where the electron's motion is governed by the familiar principles of electrostatics. B. Rutherford scattering. In the early 20th century, Ernest Rutherford studied the scattering of alpha particles, helium nuclei, by gold foil in his famous experiment. The results of this experiment led to the understanding that atoms have a dense, positively charged nucleus at their center. The classical description of the interaction between the incoming alpha particles and the nucleus was based on Rutherford scattering, where the deflection angle of the particles could be predicted by their initial energy and the nuclear charge. The key assumption in classical scattering theory is that particles interact locally, with the energy and momentum conserved in the interaction. There are no new particles created during the scattering process. The particles simply change direction due to the electromagnetic force. 2. The Mott paradox. Quantum scattering and particle creation. The role of quantum mechanics. In quantum mechanics, the behavior of particles is governed by their wave functions, which describe the probability of finding a particle in a particular state. When an electron interacts with a nucleus, the interaction is no longer purely a classical deflection. Instead, the quantum nature of the electron allows for more complex interactions, where the electron wave function can spread out and interact with the potential in a way that leads to unexpected results. This is where the Mott paradox comes into play. When an electron scatters from a nucleus, the interaction is described not just by the classical Coulomb force, but also by quantum mechanical effects, including virtual particles and field fluctuations. Under the right conditions, these quantum effects can lead to the spontaneous creation of particles, in particular, the creation of an electron-positron. The creation of electron-positron pairs. In the Mott paradox, the electron scattering from the nucleus can result in the spontaneous creation of an electron-positron pair. This process is associated with the concept of pair production, where energy is converted into mass and a particle-antiparticle pair is created. Pair production is typically a phenomenon observed in high-energy collisions, such as when a photon interacts with a strong electromagnetic field, converting into an electron and a positron. However, in the Mott paradox, the interaction is much less energetic, and the electron is scattering at relatively low energy. The fact that an electron can create an electron-positron pair during a scattering event suggests that virtual particles and field fluctuations play a much larger role in the scattering process than previously expected. C. The paradoxical aspect. Low-energy scattering. What makes the Mott paradox so striking is that electron-positron pair production typically requires high-energy interactions, such as those in gamma-ray photon collisions or high-energy particle accelerators. In the Mott paradox, the electron is scattering at relatively low energies, yet it still leads to the creation of electron-positron pairs. This seems to defy the classical and even the quantum expectations of how scattering processes should work. The paradox suggests that quantum fluctuations and virtual particles play a more profound role in the creation of particles than had been previously understood. The fact that the electron's wave function can interact with the electromagnetic field in such a way that it produces a particle-antiparticle pair raises important questions about the limits of quantum mechanics and the way energy is distributed in particle interactions. 3. Resolving the paradox. Quantum field theory and virtual particles. A. Quantum field theory and vacuum fluctuations. To resolve the Mott paradox, we turn to quantum field theory, QFT, which treats particles as excitations in underlying quantum fields. In QFT, particles such as electrons and positrons are seen as excitations in the electron field and the positron field respectively. These fields permeate all of space, and their fluctuations can lead to the creation of virtual particles, particles that appear for a brief moment and then annihilate each other. In QFT, the vacuum is not empty, but rather filled with these virtual particles. These fluctuations can interact with real particles, such as the scattering electron in the Mott paradox, leading to the creation of real electron-positron pairs. The key insight here is that virtual particles can act as intermediaries in interactions, allowing particles to momentarily access negative energy states and facilitate pair production, even in low-energy scattering events. B. The role of the electromagnetic field. In the Mott paradox, the electron's interaction with the electromagnetic field is central to the process of pair creation. The electromagnetic field can mediate the interaction between the electron and the nucleus, and in the presence of strong fields or certain conditions, the field can facilitate the creation of electron-positron pairs. This process is a manifestation of the energy-mass equivalence in quantum mechanics, where energy can be converted into particles even in relatively low-energy interactions. The fact that this process occurs in low-energy scattering suggests that the quantum vacuum itself plays an important role in the interaction. The Mott paradox serves as an early reminder of the profound effects of quantum field fluctuations and their ability to influence particle behavior in unexpected ways. 4. Implications for high-energy physics and beyond. A. Quantum electrodynamics, QED. The Moore paradox is an important concept in the development of quantum electrodynamics, QED. The theory that describes the interaction of light and matter, QED, explains how particles like electrons interact with the electromagnetic field, and it predicts processes like virtual particle creation and pair production. The Mott paradox serves as an important example of how QED can predict the creation of particles in scattering processes, even at lower energies than traditionally expected. B. Electron-positron pair production. The phenomenon of electron-positron pair production is not only a theoretical curiosity, it plays an important role in high-energy physics. For example, pair production occurs in high-energy collisions, such as those observed in particle accelerators or in astrophysical environments like black holes and gamma-ray bursts. Understanding how pair production occurs, even in low-energy scattering, can help physicists better understand the underlying processes in these extreme environments. Quantum Zeno effect paradox. Imagine you have a quantum system, such as a radioactive atom, that is decaying over time. According to classical physics, the atom will decay at a certain rate, governed by probability. But here's the paradox. If you observe the system frequently enough, the decay seems to halt or slow down dramatically. This is the quantum Zeno effect, a phenomenon in quantum mechanics where the act of continuous measurement can freeze the evolution of a quantum system. The paradox arises from the interaction between measurement and quantum state evolution. The more often we measure, the more the system seems to remain in its initial state. How can the act of observation influence the natural decay of a system? And why does frequent observation seem to prevent change when quantum systems are supposed to evolve probabilistically over time? The quantum Zeno effect paradox challenges our understanding of quantum measurement, decay processes, and the role of the observer in the evolution of quantum systems. Let's explore the quantum Zeno effect, where the act of observation seems to contradict the expected behavior of quantum systems, leading to a paradox that defies our classical understanding of decay and time. The quantum Zeno effect is named after the ancient Greek philosopher Zeno, who famously formulated paradoxes that highlighted the counterintuitive nature of motion and change. The Zeno paradoxes, such as the Achilles and the tortoise paradox, question the nature of motion by suggesting that motion is an illusion based on the paradoxical nature of infinite divisions of time and space. In the 1960s, physicists Brezin, Kemeny, and Sartori revisited Zeno's ideas in the context of quantum mechanics. They proposed that frequent measurements of a quantum system could prevent it from evolving or decaying. This phenomenon was dubbed the quantum Zeno effect, which is based on the premise that measurement collapses the wave function in quantum mechanics. According to the Copenhagen interpretation of quantum mechanics, a quantum system exists in a superposition of states until it is measured, at which point it collapses into a definite state. In 1977, physicists Misra and Sudarshan mathematically formulated the quantum Zeno effect and showed that repeated observation of a quantum system can slow down its evolution, even prevent it entirely in some cases. They used the example of a decaying particle. If the particle is constantly observed, its state remains frozen in its initial form, preventing it from decaying as expected. This is contrary to classical intuition, where a system would evolve independently of how often it is observed. The quantum Zeno effect has since become an important phenomenon in quantum mechanics, helping to explore the role of the observer in determining the state of a quantum system. It also has practical applications in fields such as quantum computing and quantum control. The quantum Zeno effect paradox challenges our understanding of how quantum systems evolve over time. The paradox arises when the act of repeated observation or measurement seems to alter the natural evolution of a system, effectively freezing or slowing down its decay. This phenomenon appears to contradict the fundamental principles of quantum mechanics, where systems are expected to evolve probabilistically over time. 1. Quantum mechanics and the evolution of quantum states. A. The Schrödinger equation and wave function collapse. In quantum mechanics, the state of a system is described by a wave function, which encodes all the possible information about the system. The wave function evolves over time according to the Schrödinger equation, which dictates how the quantum system's state changes. The Schrödinger equation is given by it equals h to the power of e, where is the reduced Planck's constant, e is the wave function of the system at time t, h to the power of is the Hamiltonian operator, which represents the total energy of the system. According to quantum theory, the wave function evolves deterministically, meaning that the probabilities of all possible outcomes of a measurement are determined by this evolution. However, when we measure a quantum system, its wave function collapses to a definite state. This collapse is instantaneous and leads to a specific outcome, even though the system was initially in a superposition of multiple possibilities. The paradox arises when we examine the role of measurement in the quantum system's evolution. In the quantum Zeno effect, continuous measurement seems to interfere with the system's natural evolution, leading to a situation where decay or change appears to be halted. B. Quantum superposition and decay. In a system undergoing quantum decay, such as a radioactive atom, the particle exists in a superposition of decayed and undecayed states. The probability of decay is governed by the exponential decay law pp equals 1 equals e, where p is the probability of decay at time t is the decay constant. Related to the half-life of the particle, in the absence of measurement, the particle is in a superposition of decayed and undecayed states, and the probability of its state evolving follows the exponential decay law. This is a fundamentally probabilistic process in quantum mechanics. C. The measurement problem. The measurement problem arises because quantum mechanics does not provide a clear explanation for what happens during the process of measurement. The wave function collapse theory, as described by the Copenhagen interpretation, suggests that when a quantum system is observed, the superposition of states collapses into one definite state. However, this collapse is a non-deterministic process, and the exact mechanism by which it occurs is not fully understood. In the context of the quantum Zeno effect, the repeated measurement of a quantum system prevents the wave function collapse from fully evolving, which means that the system does not have the chance to move from its initial state to a different state. The act of measurement appears to freeze the system in place. 2. The quantum Zeno effect. Repeated observation and its impact. A. The original Zeno paradox. The name quantum Zeno effect is inspired by Zeno's paradoxes in ancient Greek philosophy, which argued that motion is an illusion. Zeno's famous paradox of Achilles and the tortoise suggests that in order to catch the tortoise, Achilles must first reach the halfway point, then the halfway point of the remaining distance, and so on, implying an infinite series of steps that Achilles must complete before catching the tortoise. In Zeno's reasoning, this would mean that Achilles would never actually catch the tortoise. The quantum Zeno effect involves a similar concept. By repeatedly observing the state of a quantum system, it seems as though the system's evolution is frozen or delayed. The more frequent the measurements, the slower the evolution of the system appears to be, much like Zeno's paradox, where movement itself seems to be impossible due to an infinite series of steps. B. Quantum Zeno effect in action. In the quantum Zeno effect, a quantum system, such as a decaying atom, is repeatedly measured over short intervals. If the system is in a superposition of decayed and undecayed states, frequent measurements of the undecayed state can prevent the system from decaying at the expected rate. For example, if the probability of decay is given by the exponential decay law and measurements are made at frequent intervals, the wave function may be forced to collapse into the undecayed state each time. This repeated collapse essentially prevents the system from decaying, as the system does not have enough time to evolve naturally before it is measured again. The result is that the decay rate of the system slows down, or even stops altogether. C. Experimental evidence. The quantum Zeno effect has been demonstrated in several experiments, particularly in systems that involve quantum superposition and measurement. For example, in experiments involving quantum optical systems, where photons or atoms are subject to repeated measurements. The quantum state was observed to freeze or evolve more slowly due to the repeated observation. In these systems, the more frequently the system was observed, the slower the evolution of the system became. These experiments highlight the relationship between observation and the evolution of quantum states, showing that the act of measurement can fundamentally alter the natural course of events in a quantum system. 3. The paradox. Does observation halt decay? A. The implication of frozen decay. The paradoxical nature of the quantum Zeno effect lies in the fact that repeated observation, which we would normally think of as providing more information about the state of a system, actually prevents the system from changing. This is in stark contrast to classical mechanics, where observation does not affect the evolution of a system. If we think of a radioactive atom, we would expect that after a certain amount of time, the atom will have decayed according to the exponential decay law. However, when we continuously observe the atom, we might find that it has not decayed in the expected time frame. The measurement itself seems to delay or prevent the decay, which challenges our classical understanding of how time and decay should behave. B. The role of the observer in quantum mechanics. This paradox raises deeper questions about the role of the observer in quantum mechanics. Does the act of observation play a fundamental role in shaping the reality of a quantum system? In classical physics, the act of observation is passive. That in quantum mechanics, observation itself affects the outcome. The quantum Zeno effect suggests that frequent observation does not just provide information about the system, but actually influences its evolution. 4. Applications and implications for quantum computing. A. Quantum computing. The quantum Zeno effect has important implications for the field of quantum computing. In quantum computers, qubits, quantum bits, are used to perform computations. Superposition allows qubits to exist in multiple states simultaneously, providing exponential speedup for certain types of calculations. However, the act of measuring qubits can collapse their wave functions and destroy superposition. Understanding the quantum Zeno effect allows quantum computer scientists to better manage quantum coherence and quantum control, ensuring that qubits remain in superposition for long enough to perform calculations. By understanding how to utilize or avoid the quantum Zeno effect, engineers can design more stable quantum systems for computation. Schrödinger's cat paradox. Imagine a cat trapped inside a box, along with a device that has a 50% chance of releasing poison depending on the state of a radioactive atom. If the atom decays, the poison is released and the cat dies. If the atom does not decay, the cat stays alive. According to classical intuition, the cat is either alive or dead based on the state of the atom. But in the strange world of quantum mechanics, things are different. Before we observe the system, the atom is in a superposition of decayed and undecayed states, and as a result, the cat is in a superposition of being both alive and dead at the same time. This is the essence of Schrödinger's cat paradox. In quantum mechanics, the state of a system can exist in a superposition of multiple possibilities until it is observed. But this creates a paradox when applied to macroscopic objects like a cat. How can something as tangible and classical as a cat be in two contradictory states simultaneously? The Schrödinger's cat paradox challenges our understanding of measurement in quantum mechanics, and raises profound questions about the nature of reality. Let's explore the Schrödinger's cat paradox, where quantum superposition and the role of the observer collide in an unsettling and counterintuitive way. The Schrödinger's cat paradox was introduced by the Austrian physicist Erwin Schrödinger in 1935 as part of his critique of the Copenhagen interpretation of quantum mechanics, which was championed by Niels Bohr and Werner Heisenberg. Schrödinger wanted to highlight what he saw as the paradoxes and counterintuitive nature of quantum theory, especially when it came to superposition and measurement. Schrödinger's famous thought experiment involved a cat that was both alive and dead at the same time, due to the quantum state of a radioactive atom that might, or might not, decay. In the Copenhagen interpretation, the quantum system exists in a superposition of states, meaning that until the system is observed, the cat is both alive and dead. The paradox arises because this superposition of contradictory states, when applied to something as large and familiar as a cat, seems absurd and incompatible with our classical experience of the world. Schrödinger's cat was not intended to be taken literally, but rather as a conceptual tool to demonstrate the strangeness of quantum mechanics when applied to macroscopic objects. The paradox has since become a cornerstone in discussions about the measurement problem in quantum mechanics, sparking debates about wave function collapse, the role of the observer, and the boundary between the quantum and classical worlds. The Schrödinger's cat paradox remains one of the most iconic thought experiments in physics, offering a vivid illustration of the counterintuitive nature of quantum mechanics. The Schrödinger's cat paradox is a thought experiment that explores the fundamental principles of quantum mechanics, especially the concepts of superposition and measurement. The paradox arises when we extend the quantum mechanical description of small particles, like electrons, to a macroscopic system, like a cat, and encounter logical contradictions. The paradox challenges our classical intuitions about reality and raises profound questions about the nature of observation in quantum mechanics. 1. The basics of quantum mechanics, superposition and wave function. Collapse A. Superposition in quantum mechanics. In quantum mechanics, a particle can exist in a superposition of multiple states simultaneously. For example, an electron might be in a superposition of being in multiple positions at once, or an atom might be in a superposition of being decayed and undecayed. This is in stark contrast to classical physics, where objects are assumed to have definite properties and exist in one state at a time. The wave function SPs describes the quantum state of a system and encodes the probabilities of finding a system in different states. The Schrödinger equation governs how the wave function evolves over time. Before measurement, the system exists in a superposition of all possible states, and only after measurement does the wave function collapse into one definite state. For example, if we have a quantum particle, it might have a probability of being in several locations at once. The wave function is a mathematical description that captures this superposition of locations. However, once we measure the position of the particle, the wave function collapses, and the particle is found in one definite location. B. Wave function collapse and the role of the observer. In the Copenhagen interpretation of quantum mechanics, when a measurement is made, the wave function collapses into a single, definite state. Before measurement, the system exists in all possible states simultaneously, but once observed, the system chooses a specific state. This process is known as wave function collapse, and it is central to the measurement problem in quantum mechanics. The paradox emerges because the Copenhagen interpretation suggests that macroscopic systems, like a cat, should also be in a superposition of all possible states. The cat, in this case, is both alive and dead until we open the box and observe it. This creates a contradiction. How can a cat, which is a large and familiar object, be in a superposition of two mutually exclusive states? 2. Schrödinger's cat paradox. The thought experiment A. The setup of the paradox. In Schrödinger's thought experiment, the cat is placed inside a sealed box along with a radioactive atom, a Geiger counter, and a vial of poison. The setup is such that, if the radioactive atom decays, the Geiger counter triggers the release of the poison, killing the cat. If the atom does not decay, the cat remains alive. According to the Schrödinger equation, the atom is in a superposition of decayed and undecayed states until it is measured. The superposition of these two states, in turn, implies that the cat is both alive and dead at the same time, until the box is opened and an observation is made. The paradox arises because this superposition seems absurd when applied to a macroscopic object like a cat. B. The problem of macroscopic superposition. In quantum mechanics, superposition is typically observed with microscopic systems like electrons, where the system is described by a probability wave that can exist in multiple states. However, when applied to macroscopic objects, the superposition of states leads to a logical contradiction. How can an object as large and familiar as a cat be both alive and dead at the same time? The paradox is not meant to be taken literally, but rather as a way of highlighting the strangeness of quantum mechanics. Schrödinger used the thought experiment to demonstrate the limitations and counterintuitive nature of applying quantum mechanics to everyday objects. 3. Measurement and the observer effect. A. The role of the observer. The act of observation plays a central role in the quantum Zeno effect and the Schrödinger's cat paradox. According to quantum mechanics, the wave function of a system exists in a superposition of states until it is measured. This implies that the system's state is not determined until observation forces the wave function to collapse into one of the possible states. In the Schrödinger's cat paradox, the cat remains both alive and dead in a superposition until someone opens the box to observe it. At that moment, the wave function collapses and the cat is found to be either alive or dead, but not both. This raises the question, what role does the observer play in determining the state of the system? Does the consciousness of the observer influence the outcome, as some interpretations suggest? B. The measurement problem. The measurement problem in quantum mechanics is a long-standing issue, and the Schrödinger's cat paradox exemplifies this problem. If quantum systems are described by wave functions that exist in superposition, how do we reconcile this with the fact that we observe definite outcomes in the macroscopic world? The paradox questions how the quantum world, where systems can exist in multiple states, relates to the classical world, where objects are definitively either alive or dead, but not both. The Copenhagen interpretation resolves this issue by positing that the act of measurement collapses the wave function, determining the state of the system. However, this interpretation leaves open questions about what constitutes a measurement, and whether the observer plays an active role in the collapse. 4. Resolution of the paradox. Interpretations of quantum mechanics. A. The many worlds interpretation. One possible resolution to the Schrödinger's cat paradox is the many worlds interpretation, MWI, of quantum mechanics. In this interpretation, when a measurement is made, the universe splits into multiple branches, each representing a different outcome of the measurement. In the case of Schrödinger's cat, the cat would be both alive and dead in separate, non-interacting branches of the universe. Each branch corresponds to a different possible outcome, and both exist simultaneously but in different worlds. In the many worlds interpretation, there is no wave function collapse. Instead, all possible outcomes of a quantum event occur, each in a separate branch of the universe. This interpretation resolves the paradox by suggesting that the superposition of the cat's states exists in separate worlds, but does not collapse into one outcome. B. Decoherence and the role of environment. Another interpretation involves the concept of decoherence, which suggests that quantum superpositions can become effectively collapsed when a quantum system interacts with its environment. According to this view, as the cat becomes entangled with the environment, its quantum state becomes entangled with many possible outcomes. The environment essentially measures the system, leading to effective collapse without the need for a conscious observer. Decoherence provides a way of understanding how the classical world emerges from quantum mechanics. The superposition of states doesn't necessarily vanish, but the system becomes entangled with the environment in such a way that the classical outcome becomes inevitable. 5. Implications for quantum computing and technology. A. Quantum superposition in computing. The Schrödinger's cat paradox and related concepts like superposition are foundational to the field of quantum computing. In quantum computing, qubits can exist in a superposition of both 0 and 1 states simultaneously, which allows quantum computers to perform parallel computations and solve certain problems exponentially faster than classical computers. Understanding how to manipulate superpositions without causing wave function collapse is a key challenge in quantum computing. The Schrödinger's cat paradox highlights the importance of coherence in quantum systems, which must be maintained to perform useful computations. Uncertainty principle paradox. Imagine you are trying to measure the position and momentum of an electron as precisely as possible. The more accurately you determine the position, the less accurately you can know the momentum, and vice versa. This is the essence of the Heisenberg uncertainty principle, a fundamental concept in quantum mechanics that suggests there is an inherent limit to how precisely we can measure certain pairs of physical properties simultaneously. The uncertainty principle challenges our classical intuition. In classical mechanics, we assume that we can measure both position and momentum to arbitrary precision. But in quantum mechanics, the very act of measuring one property disturbs the other, creating an unavoidable trade-off between precision. This paradox forces us to confront the limits of knowledge and challenges our understanding of the nature of reality. If we cannot measure these properties exactly, what does that tell us about the world at the quantum level? How can particles exist in a state where precision is inherently limited? Let's explore the uncertainty principle paradox, where the limits of measurement collide with the intrinsic properties of quantum systems, revealing a deeper truth about the nature of the universe. The Heisenberg uncertainty principle was introduced by the German physicist Werner Heisenberg in 1927 as part of his work on quantum mechanics. The principle states that it is impossible to simultaneously measure certain pairs of conjugate variables, like position and momentum, with arbitrary precision. Heisenberg derived the uncertainty relation based on the wave nature of particles in quantum mechanics and a wave function, which describes the probability distribution of a particle's possible positions, and momenta. Heisenberg's discovery was revolutionary because it challenged the classical idea that all physical quantities can be measured with infinite precision. Before quantum mechanics, it was believed that with sufficiently advanced technology, we could measure the exact position and exact momentum of a particle at the same time. However, Heisenberg showed that this was not possible at the quantum level. The uncertainty principle is a direct consequence of the wave-particle duality of matter and the probabilistic nature of quantum mechanics. In quantum systems, particles do not have well-defined values for position and momentum until they are measured. The act of measurement itself disturbs the system and collapses the wave function, leading to the uncertainty between the two properties. Heisenberg's principle has profound implications for how we understand the nature of reality and knowledge. It also laid the foundation for further developments in quantum theory and the interpretation of quantum mechanics, particularly in relation to the role of the observer and the measurement problem. The uncertainty principle paradox is at the heart of quantum mechanics, and it forces us to reconsider the nature of knowledge and measurement in the quantum world. The paradox arises from the fact that quantum systems cannot be fully described by classical properties like position and momentum, which are assumed to be measurable with arbitrary precision in classical physics. Instead, quantum systems are governed by probabilities, and the act of measurement disturbs the system in ways that create an inherent trade-off between the precision of measurements. 1. The foundation of the uncertainty principle, A. The Heisenberg uncertainty relation. The Heisenberg uncertainty principle is mathematically expressed as dx/dp greater than equals /2, where dx is the uncertainty in position, dp is the uncertainty in momentum, is the reduced Planck constant. This inequality shows that the product of the uncertainties in position and momentum can never be smaller than a certain value /2. This is a fundamental limitation in the measurement of quantum systems and sets a limit on how precisely we can measure the properties of particles. The principle does not arise from the limitations of measurement instruments, but is an intrinsic property of quantum systems. It reveals that particles do not have definite values for certain pairs of properties, like position and momentum, until they are measured. Instead, they exist in probability distributions. B. The role of wave functions and superposition. In quantum mechanics, particles are described by wave functions, which give the probabilities of finding a particle in different states. For example, the wave function of a particle provides the probability distribution of its position and momentum. The wave function can be expressed as a superposition of multiple possible states, and the act of measurement collapses the wave function into one definite state. The uncertainty arises because the wave function of a particle spreads out over a range of positions and momenta, representing all possible locations and velocities the particle could have. When a measurement is made, the act of observation collapses the wave function into one definite outcome, but the act of measurement disturbs the system and causes the wave function to collapse to a definite value for either position or momentum, but not both, with arbitrary precision. C. The Heisenberg microscope thought experiment. Heisenberg's original thought experiment, the Heisenberg microscope, was designed to illustrate the uncertainty principle. In this scenario, an observer uses a microscope to measure the position of an electron. The microscope shines light on the electron to detect its position. However, when light interacts with the electron, it imparts momentum to the electron, altering its velocity, momentum. The more precisely the observer tries to measure the position of the electron, the greater the disturbance to its momentum. This interaction demonstrates that the act of measurement disturbs the system in a way that increases the uncertainty in the corresponding conjugate variable, momentum. Thus, the more accurately we measure one property, the less accurately we can know the other. This disturbance is an intrinsic feature of quantum mechanics and cannot be eliminated by improving measurement technology. 2. The paradox, measurement and the limits of knowledge. A. Classical versus quantum intuition. In classical physics, we assume that we can measure position and momentum of objects with arbitrary precision. If we are careful enough, we can measure the location and velocity of a car, for example, with virtually no uncertainty. However, in the quantum world, things behave differently. The uncertainty principle reveals that there is a fundamental limit to our knowledge of quantum systems. This is not due to the limitations of our measuring instruments, but due to the nature of quantum systems themselves. The paradox arises because quantum mechanics tells us that particles do not have definite positions and momentum values until they are measured, and the act of measurement inherently disturbs the system. B. The nature of knowledge in quantum mechanics. The uncertainty principle challenges the classical view of deterministic knowledge. In classical physics, we can theoretically know all properties of a system, such as position, velocity, and momentum, exactly at any given time. But in quantum mechanics, the probabilistic nature of quantum states means that we cannot simultaneously know both the position and momentum of a particle with arbitrary precision. Instead, we can only make probabilistic predictions about the outcome of a measurement. This raises deep questions about the nature of reality and the role of the observer. Does a particle have a definite position and momentum before measurement, or does the act of measurement define these properties? The uncertainty principle suggests that these quantities are not simply unknown until measured. They are fundamentally indeterminate until observed. 3. Applications of the uncertainty principle. A. Quantum tunneling. One of the key applications of the uncertainty principle is in quantum tunneling, the phenomenon where particles can pass through energy barriers that they classically should not be able to overcome. The uncertainty in a particle's momentum allows it to have a non-negligible probability of being found on the other side of the barrier, even if its energy is lower than the height of the barrier. This phenomenon is central to nuclear fusion, where the nuclei of atoms can tunnel through the Coulomb barrier to fuse, and to devices like tunnel diodes and scanning tunneling microscopes. B. Quantum computing. The uncertainty principle plays a key role in quantum computing, where qubits, quantum bits, exist in a superposition of states. This allows quantum computers to perform computations much faster than classical computers for certain tasks. However, the uncertainty in qubit states must be managed carefully to maintain the system's coherence and avoid errors due to measurement disturbances. Quantum computers rely on the manipulation of quantum superposition and entanglement, both of which are affected by the uncertainty principle. The precision of measurements in quantum computing is constrained by the limits set by the uncertainty principle, and careful control of quantum states is required to avoid collapse into a definite state before the computation is complete. See Heisenberg's microscope and measurement technology. The Heisenberg microscope serves as a reminder that measurement technology in quantum mechanics is not simply a matter of improving instruments. The uncertainty is a fundamental property of the system itself, not just a result of poor measurement techniques. This has profound implications for the development of quantum sensors, atomic clocks, and other precision measurement devices, which must account for the inherent limitations of quantum systems. 4. Philosophical implications and the nature of reality. A. The role of the observer. The uncertainty principle raises questions about the role of the observer in quantum mechanics. Does the act of measurement itself create the reality we observe, or is the system's state already determined and we simply reveal it by measuring? The Copenhagen interpretation suggests that the act of observation collapses the wave function, forcing the system into a definite state. This implies that reality is not definite until it is measured. In contrast, other interpretations, such as the many worlds interpretation, suggest that the wave function never collapses, and all possible outcomes of a quantum event occur in separate branches of the universe. The uncertainty principle plays a central role in these debates about the nature of reality and the role of measurement in quantum mechanics. Bell's spaceship paradox. Imagine two spaceships in deep space, perfectly synchronized and accelerating at the same rate. They start at rest, and the distance between them remains constant at first. But as both ships accelerate, something strange happens. The distance between them begins to change. Even though they are moving together with the same velocity, the separation between them does not stay the same. This is the Bell's spaceship paradox, which arises from the principles of special relativity and the way that acceleration and simultaneity interact in the relativistic world. According to relativity, the laws of physics are the same for all observers in uniform motion. But this paradox suggests that simultaneity, the idea that two events occur at the same time, depends on the observer's frame of reference. The paradox challenges our understanding of distance, acceleration, and simultaneity in relativity. How can two objects that are initially at rest and accelerating together end up with a change in the distance between them? Let's explore the Bell's spaceship paradox, where relativity and acceleration collide to reveal a profound and counterintuitive aspect of the fabric of space-time. The Bell's spaceship paradox was introduced by the physicist John S. Bell in 1963 as part of his work on the foundations of special relativity. Bell was interested in exploring the implications of relativity for non-inertial frames of reference, particularly frames that involve acceleration. The paradox arose from the need to understand how relativity affects simultaneity and distance when objects are accelerating in the same way. Bell's paradox is rooted in the principle of relativity, which states that the laws of physics are the same for all observers in uniform motion. However, when objects are accelerating, their behavior becomes more complicated. Bell used the example of two spaceships accelerating together at the same rate to highlight a contradiction in the way that distance between them changes. This contradiction arises due to the relativistic effects on simultaneity, the concept that two events that are simultaneous in one frame of reference may not be simultaneous in another. The Bell's spaceship paradox helps to clarify the relationship between acceleration, simultaneity, and length contraction in special relativity. The paradox has been widely discussed in relativity and spacetime studies, illustrating the counterintuitive nature of spacetime geometry and the way non-inertial frames of reference must be treated in relativity. The Bell's spaceship paradox is a thought experiment that illustrates the strange and counterintuitive effects of special relativity on accelerating objects. At its core, the paradox challenges our understanding of simultaneity, distance, and motion in the relativistic context. The paradox highlights a key feature of relativity, the way that space-time geometry behaves when objects undergo acceleration rather than moving at a constant velocity. 1. Special relativity, the basics. A. The principle of relativity. At the heart of special relativity is the principle of relativity, which states that the laws of physics are the same for all observers in uniform motion. This principle was first articulated by Galileo Galilei and later extended by Albert Einstein in his theory of special relativity. According to this principle, there is no privileged frame of reference, and the laws of physics should be invariant in all inertial frames, those that are not accelerating. Special relativity also introduced the concept of space-time, where time and space are treated as a unified four-dimensional continuum. In this framework, the distance between two events is given by the space-time interval, which is the same for all observers, regardless of their relative motion. B. Simultaneity in relativity. A key concept in special relativity is simultaneity. The idea that two events can occur at the same time in one frame of reference but may not appear simultaneous in another frame moving relative to the first. This is a direct consequence of the relativity of simultaneity, which states that there is no universal notion of simultaneity across all frames of reference. Events that appear simultaneous to one observer may not be simultaneous to another observer in motion relative to the first. This effect is one of the most striking consequences of special relativity, as it contradicts our classical intuition about the absolute nature of time. It shows that time is not an independent universal flow, but rather depends on the relative motion of observers. 2. The setup of Bell's spaceship paradox. A. Two spaceships in deep space. In Bell's thought experiment, we imagine two spaceships that are initially at rest relative to each other in deep space. These two ships are identical and are equipped with a mechanism that allows them to accelerate at the same rate in the same direction. The key aspect of the setup is that the acceleration of the two ships is perfectly synchronized, so the distance between the ships remains constant at first. In classical mechanics, we would expect that if both spaceships are accelerating at the same rate, the distance between them would remain unchanged. Since both ships are subjected to the same acceleration, they should remain at the same separation distance. However, the paradox arises when we take into account the relativistic effects of acceleration and simultaneity. B. The expectation of constant distance. According to classical physics, the acceleration of both spaceships should cause them to move together as a unit, with the distance between them remaining constant. The idea is that if two objects are accelerating at the same rate, they should both experience the same increase in velocity, and the distance between them should remain unchanged. In classical physics, this scenario would be unremarkable. Two objects accelerating in tandem would simply stay at the same relative distance. However, in the relativistic context, things get more complicated. Relativity suggests that the behavior of the spaceships will be influenced by the way simultaneity works in different frames of reference, and this leads to surprising results. 3. Relativity and the change in distance between the spaceships. A. Length contraction and accelerating frames. In special relativity, one of the key predictions is length contraction. The length of an object moving at high speeds will appear contracted in the direction of motion when observed from a stationary reference frame. This contraction occurs due to the Lorentz transformation, which describes how space and time are altered when an object is moving at speeds close to the speed of light. When the two spaceships in Bell's paradox accelerate, they move at increasing velocities relative to an observer at rest. According to relativity, each spaceship will experience length contraction as it accelerates. However, because the two ships are accelerating together, the relativistic effects will be synchronized, meaning that the distance between the two ships will not remain constant as they accelerate. The key point is that in the reference frame of the ships, the distance between them should remain constant. However, the observers who measure the system from an external frame will see that the distance between the ships decreases due to relativistic effect. This discrepancy arises from the fact that simultaneity is not preserved across frames of reference. B. The relativity of simultaneity and the breaking of synchronization. The relativity of simultaneity plays a crucial role in the paradox. In the reference frame of an observer outside the accelerating system, the events that occur on the two ships, such as measurements of their positions, will not appear to be simultaneous. This is because the relativity of simultaneity tells us that what one observer perceives as a simultaneous event may not be seen as simultaneous by another observer moving relative to the first. In Bell's paradox, this means that the observers on the two ships will not agree on the positions of the ships at any given time. Even though the ships are accelerating at the same rate, their simultaneous positions in one reference frame do not remain in sync across different frames. This leads to the surprising result that the distance between the ships changes as they accelerate, even though they are moving together at the same rate. 4. The paradox, the distance between the spaceships. A. The acceleration-induced separation. In classical mechanics, the two ships should remain at the same distance from each other as they accelerate together. However, in the relativistic context, the distance between the ships increases. This is due to the fact that the events that happen at each spaceship, such as the measurement of their distance, are not simultaneous in all frames of reference. The Lorentz transformation reveals that, in the external observer's frame, the ship's positions are not in sync, and this causes the relative separation to increase. The paradox is that, according to special relativity, even though the two ships are accelerating in exactly the same way, the distance between them changes due to the relativity of simultaneity and the way that length contraction works in the accelerating reference frame. B. The contradiction with classical expectations. The Bell's spaceship paradox highlights the counterintuitive nature of special relativity. It shows that even though two objects may accelerate in the same way, their relative positions may not remain constant. This result contradicts our classical intuition, where we expect the two ships to maintain a constant distance while accelerating. The relativistic effects of simultaneity and length contraction lead to a surprising result. The ships' positions are not as synchronized as we would expect. 5. Resolution of the paradox A. Understanding simultaneity in accelerating frames. The resolution of the Bell's spaceship paradox lies in understanding the concept of simultaneity in special relativity. The paradox arises because the assumption that the ships maintain a synchronized separation is only valid in the frame of reference of the ships themselves. When viewed from an external reference frame, the events on the ships are no longer simultaneous, leading to an apparent increase in the distance between the ships. B. The role of Lorentz transformations. The key to resolving the paradox is understanding how Lorentz transformations govern the behavior of objects in relativistic contexts. The Lorentz transformation shows how length contraction and time dilation affect the measurements of distances and times between events in different frames of reference. The relativity of simultaneity ensures that, in the external frame, the two ships will not remain in perfect synchronization. 6. The implications for relativity and accelerating objects. A. Non-inertial frames and space-time curvature. The Bell's spaceship paradox also helps us understand how non-inertial frames of reference behave in relativity. When objects are accelerating, their motion is not described by the usual Lorentz transformations that apply to inertial frames that are not accelerating. The paradox illustrates how accelerating frames lead to complicated effects on simultaneity and separation distances, even when the objects are accelerating together at the same rate. B. Insights into space-time geometry. The paradox emphasizes the complexity of space-time geometry in relativity and the way accelerating objects behave. It provides insight into the relativistic effects that arise when objects are not moving at constant velocities, but are instead subject to forces that change their speed. Relation paradox. Imagine you throw an object into a black hole, a region of space where gravity is so strong that nothing, not even light, can escape. The object disappears beyond the event horizon, the point beyond which nothing can return. According to general relativity, once something crosses the event horizon, all information about it is lost to the universe. However, quantum mechanics suggests that information can never truly be lost, as it is conserved in all physical processes. This leads to the black hole information paradox. If information is lost inside a black hole, it would violate the principle of quantum mechanics that information must be preserved. On the other hand, if information is preserved, it suggests that black holes might not behave as general relativity predicts. The paradox challenges our understanding of gravity, quantum mechanics, and the nature of space-time itself. Can information really be lost in black holes? Or is there a deeper connection between quantum mechanics and general relativity that we have yet to understand? Let's dive into the black hole information paradox, where quantum theory, gravity, and the fate of information collide in a deep mystery of modern physics. The black hole information paradox emerged in the 1970s, following the discovery of Hawking radiation by theoretical physicist Stephen Hawking. Hawking showed that black holes are not completely black. Instead, they emit thermal radiation due to quantum effects near the event horizon. This radiation leads to the gradual evaporation of black holes over time. The key issue, however, is that Hawking radiation appears to be completely random, with no discernible connection to the matter that originally fell into the black hole. This suggests that the information contained within the infalling matter is lost during the evaporation process, which conflicts with the principle of quantum mechanics. In quantum mechanics, the unitary evolution of the wave function requires that information about all physical systems is preserved. Nothing can truly disappear. This created a paradox. If black holes could evaporate and lose information, it would violate a fundamental rule of quantum theory. This paradox has spurred much debate, with physicists exploring various resolutions, including ideas like the holographic principle, suggesting that information is encoded on the event horizon, black hole complementarity, and the idea that information may be stored in quantum correlations within the radiation, the paradox remains one of the most profound unresolved issues in physics. It highlights the difficulty of reconciling quantum mechanics and general relativity, two of the pillars of modern physics that, as of now, remain incompatible in certain extreme conditions like those found inside black holes. The black hole information paradox presents one of the most intriguing and unresolved issues in modern theoretical physics. At the heart of the paradox lies the seeming contradiction between general relativity, which governs the behavior of black holes, and quantum mechanics, which governs the behavior of subatomic particles. The paradox challenges our understanding of space-time, gravity, and the conservation of information, highlighting the tension between these two fundamental theories of nature. 1. General relativity and black holes. Black holes and event horizons. In general relativity, a black hole is a region of space where the gravitational field is so strong that not even light can escape from it. The boundary of this region is called the event horizon, the point beyond which nothing can return. Anything that crosses the event horizon, whether it's a particle, light, or information, is lost to the outside universe. The immense gravitational pull near the event horizon warps space-time to such an extent that it effectively seals off any possibility of communication with the rest of the universe. According to general relativity, once something falls into a black hole, it is irreversibly trapped. Any information about the particle or object, whether it's its position, momentum, or other properties, appears to be destroyed as it moves beyond the event horizon. In this view, the black hole behaves as a one-way trap for matter and energy, and all that remains is the mass, charge, and angular momentum of the black hole, which can be described by a few parameters. B. Hawking radiation and the loss of information. In the 1970s, Stephen Hawking made a groundbreaking discovery. He showed that black holes could emit thermal radiation due to quantum effects near the event horizon, a phenomenon now known as Hawking radiation. This radiation arises because of quantum fluctuations that create virtual particle pairs near the event horizon. One of these particles falls into the black hole, while the other escapes as radiation. Over time, this radiation leads to the gradual evaporation of the black hole. The key issue with Hawking radiation is that it appears to be completely random and unrelated to the information that originally fell into the black hole. If a black hole slowly evaporates and releases radiation without any information about its contents being carried away, it suggests that the information contained in the black hole has been lost forever. This leads to a conflict with quantum mechanics, which dictates that information must be preserved in all physical processes, including the evolution of quantum states. 2. The paradox, the conflict between quantum mechanics and general relativity. A. The principle of unitarity in quantum mechanics. In quantum mechanics, the principle of unitary evolution dictates that the total information about a system must be preserved over time. This means that even though a quantum system can evolve in a probabilistic way, the total amount of information about the system remains conserved. The wave function of the system evolves deterministically according to the Schrödinger equation, and there is no mechanism in quantum theory that allows for the loss of information. The black hole information paradox arises because the loss of information due to black hole evaporation seems to contradict the unitary nature of quantum mechanics. If information is truly lost when an object falls into a black hole, and the black hole evaporates via Hawking radiation, this would violate a fundamental principle of quantum theory, that information is never destroyed. This paradox creates a profound conflict between the two pillars of modern physics: general relativity, which predicts that information can be lost inside black holes, and quantum mechanics, which insists that information is always conserved. B. So the no-hair theorem and information loss, the no-hair theorem in general relativity, states that once matter falls into a black hole, all the distinguishing information about it is lost except for a few macroscopic properties such as mass, charge, and angular momentum. According to this theorem, the black hole itself is described by a relatively simple set of parameters, and once matter crosses the event horizon, the specifics of that matter's identity become irrelevant. This implies that once a particle or object falls into a black hole, its information is permanently lost. The no-hair theorem directly conflicts with the principles of quantum mechanics, which state that no information can be destroyed, leading to the information paradox. 3. Possible resolutions to the paradox. A. The holographic principle 1. Of the most promising resolutions to the black hole information paradox is the holographic principle, which suggests that all information inside a black hole may be encoded on its event horizon. According to this idea, the information about the black hole's contents is not lost, but rather is stored in a two-dimensional form on the surface of the event horizon. This principle arose from studies in string theory and quantum gravity, and it suggests that the three-dimensional world we observe may be a projection of information encoded on a two-dimensional surface. The holographic principle provides a way to reconcile the loss of information inside a black hole with the preservation of information in quantum mechanics. According to this view, while the information may be hidden inside the black hole, it is not lost. It is simply encoded in a different form on the horizon. This could mean that the radiation emitted by black holes contains all the information that fell into the black hole, albeit in a highly scrambled form. B. Black hole complementarity. Another potential resolution is black hole complementarity, a theory proposed by Leonard Susskind and others. According to this idea, information about matter that falls into a black hole is both lost to the external observer and simultaneously encoded in the radiation emitted by the black hole. This suggests that different observers may have different descriptions of the system, but the total information is preserved. In this scenario, an observer falling into the black hole would experience the information loss in one way, while an external observer would perceive the information as being encoded in the radiation. This view resolves the paradox by suggesting that the loss of information is not absolute, but depends on the observer's perspective. C. Information in quantum correlations. Some physicists have proposed that the information about the matter inside a black hole might be stored in quantum correlations between the black hole's interior and the Hawking radiation emitted. This approach suggests that entanglement and quantum correlations could carry the missing information, potentially allowing for the reconstruction of the lost information from the radiation itself. This idea is still a topic of debate, but points to the quantum entanglement that is fundamental to quantum mechanics. 4. Implications for the nature of space-time and quantum gravity. A. The quest for quantum gravity, the black hole information paradox, highlights the need for a theory of quantum gravity, which would merge general relativity and quantum mechanics into a single framework. Current theories such as string theory and loop quantum gravity aim to describe the quantum properties of space-time itself, and could potentially resolve the paradox. One of the key challenges in developing quantum gravity is understanding how information is preserved in extreme conditions like those inside black holes. The resolution of the black hole information paradox could offer profound insights into the true nature of space-time, gravity, and quantum mechanics. Gibbs paradox. Imagine you have a box filled with two different gases, say gas A and gas B, separated by a partition. The gases are distinct, and they occupy different regions of the box. Now, remove the partition and let the gases mix freely. According to statistical mechanics, the total entropy of the system should increase as the gases move toward a more probable mixed state. However, a strange issue arises. If the particles of gas A and gas B are indistinguishable from each other, the entropy increase seems to be too large. This is the essence of the Gibbs paradox, a contradiction between the classical prediction of entropy increase and the reality of indistinguishable particles in quantum mechanics. Why does entropy behave differently when particles are distinguishable versus when they are indistinguishable? The paradox challenges our understanding of the fundamental nature of particles, entropy, and thermodynamics. How can we reconcile the classical ideas of entropy with the quantum behavior of indistinguishable particles? Let's explore the Gibbs paradox, where the seemingly straightforward calculation of entropy runs into counterintuitive results when quantum mechanics is taken into account. The Gibbs paradox was first introduced by the American physicist Josiah Willard Gibbs in the late 19th century. Gibbs was a pioneer in the development of statistical mechanics, the branch of physics that explains thermodynamic behavior in terms of microscopic states and probabilities. In his work on entropy, Gibbs explored how the entropy of a system changes when two gases are allowed to mix. The paradox arises when considering the entropy change during the mixing of two distinct gases in a box. If the gases are considered distinguishable, statistical mechanics predicts a certain increase in entropy. However, when the gases are indistinguishable, the expected entropy increase should be smaller. This apparent contradiction led to the realization that the indistinguishability of particles should be taken into account when calculating entropy in thermodynamics. In classical thermodynamics, the mixing of gases is treated as an increase in disorder, leading to an increase in entropy. However, when particles are indistinguishable, as in the case of quantum particles, the calculation of entropy becomes more subtle. The Gibbs paradox highlights the need for a more refined understanding of indistinguishable particles and their behavior in statistical mechanics, which would later be addressed through quantum statistics. The resolution of the Gibbs paradox laid the foundation for the development of quantum statistical mechanics, which describes the behavior of particles, such as bosons and fermions, in terms of their indistinguishability. The Gibbs paradox exposes a deep issue in the classical calculation of entropy and its relationship to the distinguishability of particles. The paradox arose when classical statistical mechanics was applied to mixtures of gases. It also laid the groundwork for the later development of quantum statistical mechanics, which accounts for the indistinguishability of particles at a microscopic level. The resolution of the paradox highlights the crucial difference between classical and quantum statistical treatments of particles. 1. Classical statistical mechanics and entropy. A. The concept of entropy, introduced by Ludwig Boltzmann and Clausius, is a measure of the disorder or randomness in a system. In classical thermodynamics, the entropy change ds of a system is related to the amount of heat transferred Q divided by the temperature T ds equals Q/T. This definition works for macroscopic systems and is based on thermodynamic properties. In statistical mechanics, entropy can be understood in terms of the number of possible microscopic states, O, of a system. The statistical definition of entropy, derived by Boltzmann, is S equals K U B M N O, where S is the entropy, Kg is the Boltzmann constant, B. O is the number of possible microscopic states of the system. This formula links entropy to the number of possible configurations or microstates of the system. The greater the number of accessible states, the higher the entropy. In systems where particles can be distinguished, this calculation is straightforward, as each particle can be treated as a separate entity with its own state. B. The entropy of mixing distinguishable gases. In the case of two distinct gases, A and B, each consisting of distinguishable particles, the entropy change, ds, upon mixing is calculated by considering the individual states of each gas. If the gases are initially separated, there is a certain number of microscopic configurations that correspond to the gas being confined to one side of the container. When the partition is removed and the gases are allowed to mix, the number of accessible microstates increases, and thus the entropy increases. For two distinguishable gases, A and B, the total number of microstates available to the system increases by a factor of O, OB, where OA and OB represent the number of accessible states of gases A and B respectively. The change in entropy upon mixing is ds equals minus n Rxa plus xb ln xb, where n is the number of moles, R is the gas constant, Xa and Xb are the mole fractions of gases A and B. This entropy change assumes that the two gases are distinguishable, and the calculation is based on classical statistical mechanics. 2. The paradox. Indistinguishable particles A. The assumption of indistinguishability. The Gibbs paradox arises when we treat the particles of the gases as indistinguishable. In quantum mechanics, indistinguishability means that particles of the same type, e.g. electrons or photons, cannot be labelled or differentiated from one another. This is fundamentally different from classical mechanics, where we assume that all particles can be tagged with unique label. When particles are indistinguishable, the number of possible microstates is not simply the product of the individual states of each gas, because the particles cannot be treated as independent entities. This affects the way we calculate the total number of accessible states, and consequently, the entropy. The entropy of mixing indistinguishable gases, in the case of indistinguishable particles, the number of accessible microstates is reduced because swapping particles between the two gases does not produce a new configuration. In classical statistical mechanics, when gas A and gas B mix, the entropy change depends on the fact that we treat each particle as distinguishable. However, when the particles are indistinguishable, the number of distinct configurations of the system decreases. This leads to the paradox. When treating the gases as indistinguishable, the increase in entropy upon mixing is smaller than it would be for distinguishable particles, even though the same physical process mixing is happening. The difference in the predicted entropy change between distinguishable and indistinguishable particles is the core of the Gibbs paradox. 3. Resolution of the paradox. Quantum statistical mechanics. A. Quantum statistical treatment. The resolution of the Gibbs paradox comes from quantum statistical mechanics, which treats indistinguishable particles according to their quantum properties. In quantum mechanics, particles are categorized as either bosons, particles that obey Bose-Einstein statistics, or fermions, particles that obey Fermi-Dirac statistics. For indistinguishable particles, the Pauli exclusion principle for fermions, or Bose-Einstein condensation for bosons, dictates the way particles can be distributed among available quantum states. For bosons, multiple particles can occupy the same quantum state, leading to Bose-Einstein condensation in some conditions. For fermions, the Pauli exclusion principle prevents more than one particle from occupying the same quantum state. In quantum statistical mechanics, the partition function Z that counts the number of available states is modified to account for indistinguishability. The corrected partition function includes a factor of symmetry that adjusts for the indistinguishability of particles, ensuring that the entropy calculations are consistent with quantum principles. This resolves the paradox by showing that the entropy increase is not as large as the classical calculation suggests, because we must account for the indistinguishability of particles. B. The role of entropy in quantum systems. The entropy in a quantum system that consists of indistinguishable particles is lower than that in a classical system of distinguishable particles. The Gibbs paradox disappears once we apply the correct quantum treatment of indistinguishable particles, which properly accounts for the way particles are distributed among quantum states. By modifying the classical entropy calculation with quantum statistics, we obtain the correct entropy for the system, reconciling the paradox. 4. Implications of the Gibbs paradox for thermodynamics and quantum mechanics. A. The nature of indistinguishable particles. The Gibbs paradox highlights the importance of indistinguishability in quantum mechanics. It shows that the classical assumption that particles are distinguishable does not hold at the quantum level. This distinction between classical and quantum statistical mechanics is crucial for understanding the statistical behavior of gases and other systems at the microscopic scale. B. The holographic principle and information theory. The Gibbs paradox also ties into broader discussions about information theory and the holographic principle in physics. The paradox emphasizes the role of quantum information and how it is distributed among the particles in a system. Understanding how information is encoded in quantum states and how it is preserved or lost is a fundamental question in modern physics, particularly in the study of black holes and quantum gravity. Ladder paradox. Imagine a ladder that is longer than a garage in which it is supposed to fit. If the ladder is moving fast enough, it might seem like it should be able to fit inside the garage. After all, the ladder's length is greater than the length of the garage when measured in the ladder's rest frame. But according to special relativity, objects moving at high speeds experience length contraction, meaning the ladder's length will appear shorter from the perspective of an observer at rest in the garage. This presents a paradox. In the ladder's own rest frame, it's too long to fit inside the garage, yet in the garage's rest frame, it appears contracted and can fit. How can both these observations be true at the same time? How can the ladder be both too long and short enough to fit in the garage? The ladder paradox forces us to confront the strange effects of special relativity, particularly when it comes to simultaneity and the relativity of length. What happens when objects seem to contradict themselves depending on the observer's frame of reference? Let's explore the ladder paradox, where motion and relativity combine in a thought-provoking and counterintuitive scenario. The ladder paradox, also known as the relativity of length paradox, was introduced as a thought experiment in the context of special relativity to explore the effects of length contraction and simultaneity. While the paradox itself was not originally formulated by Einstein, it arises naturally from the principles of special relativity and is often discussed in texts related to space-time and relativity. The paradox involves a ladder that is longer than the garage into which it is supposed to fit. When the ladder is at rest in its own frame, it is clearly too long to fit inside the garage. However, when the ladder moves with a high velocity, the observer in the garage frame sees the ladder undergo length contraction. According to special relativity, objects moving at high speeds will appear shorter in the direction of motion. This means that from the perspective of the garage observer, the ladder should fit into the garage, even though it seemed too long when at rest. The paradox highlights the fact that simultaneity, the idea that events happening at the same time in one frame of reference are not necessarily simultaneous in another frame, leads to a seemingly contradictory situation. This paradox sheds light on the counterintuitive effects of relativity, especially in non-inertial frames and with moving objects. The latter paradox is often used to help illustrate key concepts in relativity, such as the relativity of simultaneity, length contraction, and the different perspectives of observers in different frames of reference. The latter paradox is a thought experiment in special relativity that challenges our intuition about how lengths behave in different reference frames. The paradox arises when we consider an object, the ladder, moving at high speed relative to an observer at rest in the garage, where the object's length contracts due to the effects of special relativity. 1. Basic setup of the paradox. A. The ladder and garage scenario. In the setup, we have a ladder that is longer than the garage when at rest. The ladder moves at high speed toward the garage, moving in the direction of its length. The observer in the garage watches the ladder move at high velocity. In the ladder's rest frame, it is clear that the ladder is too long to fit into the garage, since its length exceeds that of the garage. The paradox begins when we consider the garage frame, where the ladder is moving at high velocity. B. Length contraction in special relativity. In special relativity, one of the core principles is length contraction. An object moving at a high speed will appear shorter along the direction of its motion when observed from a frame in which the object is moving. This effect becomes significant as the object approaches the speed of light. Mathematically, the length contraction is given by the formula L equals L0 / 1 minus V2 / C2, where L0 is the proper length of the object, its length at rest, L is the contracted length, the length observed by an observer moving relative to the object, v is the velocity of the object relative to the observer, c is the speed of light. According to the theory of special relativity, as the ladder moves toward the garage, its length will contract along the direction of motion. From the perspective of the observer in the garage, the ladder will appear shorter than its length in its own rest frame. 2. The paradox. What happens in the garage frame? A. The ladder in the garage's rest frame. From the perspective of an observer in the garage's rest frame, the ladder is moving at high speed. As the ladder moves, its length contracts due to length contraction. The observer in the garage will see the ladder as shorter than it would appear if it were at rest. This suggests that, at least in the garage frame, the ladder should fit perfectly inside the garage, even though it was too long to fit when it was at rest. So, from the garage's frame of reference, the ladder can now fit entirely inside the garage. B. Simultaneity and the ladder's length. The paradox comes into full effect when we consider the concept of simultaneity. According to special relativity, events that appear simultaneous in one reference frame may not appear simultaneous in another reference frame. This is called the relativity of simultaneity. In the ladder's rest frame, we can imagine the ladder as being composed of parts that are all simultaneously at rest and aligned end to end. But in the garage's rest frame, things are different. The ladder's moving parts experience different times at different locations due to the relativity of simultaneity. This means that the front and rear ends of the ladder, from the perspective of the observer in the garage, do not appear to be aligned in the same way that they do in the ladder's rest frame. For instance, when the front of the ladder reaches the end of the garage, the back of the ladder has not yet reached the beginning of the garage due to the relativity of simultaneity. So, although the ladder appears to be contracted, it is still not able to fit entirely inside the garage at a single moment in the garage's reference frame. 3. Resolving the paradox. A deeper look into length contraction and simultaneity. A. The key point of the paradox. Inconsistent lengths. The central issue of the ladder paradox lies in the fact that length contraction and simultaneity do not work the way classical intuition would suggest. From the garage frame, the ladder's length is contracted, and the distance between the ends of the ladder seems to shrink. However, due to the relativity of simultaneity, the two ends of the ladder are not measured at the same time in the garage's reference frame. This means that although the ladder's length appears shorter in the garage frame, the distance between its front and back ends cannot be measured simultaneously from the perspective of the observer in the garage. Thus, the ladder cannot simultaneously fit inside the garage from the perspective of the external observer, even though in the ladder's rest frame it is too long to fit. B. Length contraction and relativity of simultaneity. In the ladder's rest frame, the ladder's length is constant, and the front and rear ends are simultaneously in position. However, in the garage frame, the length of the ladder is contracted, but this contraction does not happen uniformly, because the positions of the two ends are not measured simultaneously due to relativistic effects. The paradox demonstrates the non-intuitive nature of relativistic transformations. The events that seem simultaneous in the ladder's rest frame, the two ends of the ladder being aligned, are not simultaneous in the garage's frame, leading to the apparent contradiction between the two observers. 4. The resolution. No contradiction, just different perspectives. A. Consistency of relativistic physics. While the paradox appears to create a contradiction, the resolution lies in the fact that special relativity is fully consistent. Both observers, one in the garage and one on the ladder, agree on the laws of physics, and each observer sees the other's frame as moving. The simultaneity and length contraction effects differ between frames, but there is no actual contradiction. The ladder's contracted length in the garage frame is consistent with the fact that the two ends of the ladder are not simultaneous in the garage frame, even though the ladder appears to fit in the garage. From the garage's perspective, the relative motion causes the distance between the ends of the ladder to remain inconsistent due to the relativistic effects on simultaneity. B. No violation of physics. Ultimately, the ladder paradox does not violate any physical laws. It simply reveals how special relativity alters our classical understanding of space and time. The paradox is a reminder that space-time is relative, and that the geometry of moving objects must be understood through the framework of relativity, not classical intuition. Meccano's velocity composition paradox. Imagine you are on a train moving at a constant speed, and you observe an object moving inside the train at a certain velocity. Now, let's say the train is moving relative to an observer outside the train at a different velocity. According to special relativity, the velocities we observe in different frames are not simply added together in the classical sense. Instead, the velocity composition must follow a specific formula, known as the relativistic velocity addition formula. However, in the context of Meccano's velocity composition paradox, a seemingly simple scenario of relative motion leads to counterintuitive results. If you try to calculate the relative velocities between two objects using classical methods, you get results that seem to contradict the relativistic formula, showing that velocities do not simply add linearly. The paradox highlights the difference between classical mechanics and special relativity, raising important questions about how velocity should be composed when objects are moving at significant fractions of the speed of light. How can we reconcile our everyday understanding of motion with the strange behavior of relativity when velocities approach the speed of light? Let's explore the Meccano's velocity composition paradox, where relative motion and velocity addition collide in a thought-provoking and counterintuitive scenario. The Meccano's velocity composition paradox is a thought experiment that was introduced by the physicist Meccano to explore the implications of special relativity on velocity addition. The paradox arises from the tension between classical velocity addition and the relativistic velocity addition formula, which governs how velocities combine when objects are moving at high speeds relative to each other. In classical mechanics, velocity is simply added according to the familiar formula v_vrel equals vv plus v, where vrl is the relative velocity between two objects, v and v are the velocities of the objects relative to a common reference frame. However, when objects move close to the speed of light, the classical formula fails and we must use the relativistic velocity addition formula v_vrel equals vvb slash c to the power of 2, where c is the speed of light. The paradox arises because, when we apply the classical formula in high-speed scenarios, the results do not match the predictions of special relativity. Meccano's thought experiment focuses on this discrepancy, showing how classical intuition about velocity addition breaks down in the relativistic regime. The velocity composition paradox forces us to confront the strange nature of relative motion and the limits of classical mechanics in high-speed regimes, laying the groundwork for a deeper understanding of special relativity and the fundamental nature of motion. The Meccano's velocity composition paradox highlights the counterintuitive effects of relativistic velocities and how our classical understanding of velocity addition breaks down at high speeds. This paradox illustrates how special relativity forces us to rethink basic concepts of relative motion and velocity composition when objects are moving at significant fractions of the speed of light. 1. Classical mechanics and velocity addition. A. Classical velocity addition. In classical mechanics, the relative velocity between two objects is simply the sum of their velocities. This can be seen in the following equation. V vrel equals VV plus VV, where V vrel is the relative velocity between two objects A and B, V is the velocity of object A, VV is the velocity of object B. This rule works well when the velocities involved are much smaller than the speed of light. For example, if a car moves at 60 km/h relative to the ground and a passenger inside the car walks at 5 km/h, the passenger's speed relative to the ground would be simply 65 equals 65 km/h. The classical velocity addition formula assumes that time and space are absolute, that is, the same for all observers regardless of their motion. When velocities are low, i.e. far below the speed of light, this simple addition rule works perfectly well. B. The limitation of classical addition at high velocities. As objects move faster and closer to the speed of light, the classical approach to velocity addition begins to break down. According to special relativity, no object can move faster than the speed of light. The classical velocity addition formula, which assumes that velocities simply add together, does not account for the fact that velocities approach a limit, the speed of light, and cannot exceed it. The paradox arises when we attempt to apply this classical formula to relativistic speeds, that is, speeds that are a significant fraction of the speed of light. 2. The relativistic velocity addition formula, A. The relativistic formula for velocity addition. In special relativity, the addition of velocities is governed by the relativistic velocity addition formula, which accounts for the finite speed of light and the fact that space and time are not absolute. The formula for the relative velocity v vrel between two objects moving at velocities va and vv relative to an observer is vrel equals va plus vb slash 1 plus vav b slash c to the power of 2, where v vrel is the relative velocity between the two objects, va and v are the velocities of the objects relative to a common reference frame, c is the speed of light. B. Key differences between classical and relativistic addition. The relativistic velocity addition formula differs from the classical formula in the denominator, which introduces a correction factor that prevents the relative velocity from exceeding the speed of light. The correction factor is given by 1 plus VAVB slash c to the power of 2. This factor ensures that even if both velocity VAVB are close to the speed of light, the resulting relative velocity VAVB are close to the speed of light, the speed of c. The consequence of high velocities. When VA and VB are much smaller than c, the relativistic velocity addition formula approximates the classical formula, since VAVB slash c to the power of 2 becomes negligible. However, as VA and VB approach c, the relativistic formula predicts that the resulting velocity VRL will approach the speed of light, but will never exceed it. This behavior differs dramatically from the classical approach, where velocities would simply add, leading to a velocity larger than c if both objects were moving at speeds close to c. 3. Meccano's paradox. The relativistic breakdown of classical intuition. A. The paradox setup, Meccano's paradox, involves a scenario in which two objects are moving relative to each other at relativistic speeds. The goal is to determine their relative velocity from the perspective of an observer in a third frame. When using the classical velocity addition formula, we might expect the relative velocity to simply be the sum of the two velocities. However, when we apply the relativistic velocity addition formula, we find that the velocities don't add linearly. For example, imagine two objects, A and B, moving at speeds VA and VV relative to an observer. In classical mechanics, their relative velocity VRE is Vrl equals var plus VA plus V. But in relativity, the same velocities would give a relative velocity VRE given by Vrl equals var plus VAB slash plus 1 plus VAV B slash c to the power of 2. When we substitute values near the speed of light for var and VV, the difference between the classical and relativistic calculations becomes significant, and the classical intuition breaks down. B. The paradoxical result. The Mercurnu paradox arises when we observe the discrepancy between the classical and relativistic results. The classical formula suggests that relative velocities should simply add, but the relativistic formula shows that velocities approach the speed of light but never exceed it. This leads to the paradoxical conclusion that classical velocity addition no longer works at relativistic speeds, and the simple rule we use for everyday speeds is no longer valid in high-speed scenarios. The paradox highlights the strange nature of relative motion and the limits imposed by special relativity on how we can combine velocities. 4. Implications of the Mercurnu paradox. A. The need for relativity in high-speed motion. The Mercurnu paradox illustrates that classical mechanics and the classical understanding of motion break down at high velocities. It forces us to accept that special relativity provides the correct framework for understanding relative motion at relativistic speeds. The paradox helps reinforce the idea that velocity addition is not simply an algebraic sum at high speeds, but rather follows a more complex relationship that ensures the speed of light is never surpassed. B. Relativity and non-intuitive results. The Mercurnu paradox is a stark reminder of how special relativity leads to non-intuitive results that contradict our everyday understanding of motion. The fact that velocities don't simply add at high speeds challenges classical physics, forcing us to rethink how we understand relative motion in the context of relativity. C. The role of observers in relativity. The paradox also highlights the importance of the frame of reference in relativistic calculations. Unlike classical mechanics, where the velocity of an object is an absolute quantity, in special relativity, velocities are always measured relative to a specific observer's frame. This adds another layer of complexity to our understanding of motion, especially when dealing with objects moving at relativistic speeds. The train wreck of radiation, of charged particles. Imagine a charged particle, such as an electron, moving through space. According to classical electrodynamics, any accelerating charged particle should radiate electromagnetic energy in the form of electromagnetic radiation, which means the particle loses energy as it moves. But here's the paradox. How can a charged particle keep moving indefinitely if it continuously loses energy through radiation? In fact, if this theory holds true, the particle should eventually spiral inward and collapse, losing all its energy. However, in reality, charged particles, such as electrons, orbit atoms for long periods without radiating away all their energy. This apparent contradiction is the paradox of radiation of charged particles, a fundamental problem in classical electromagnetism that highlights the limits of classical theory in explaining the behavior of particles at small scales. If electrons are supposed to radiate energy and lose their momentum, how do atoms remain stable? This paradox was one of the key issues leading to the development of quantum mechanics, which introduced new principles for understanding the behavior of particles and their interactions with electromagnetic fields. Let's explore the paradox of radiation, of charged particles, where energy loss and stability clash in a thought-provoking conundrum. The paradox of radiation of charged particles arose in the early 20th century as physicists tried to understand the behavior of charged particles moving in an electromagnetic field. According to James Clerk Maxwell's equations for electromagnetism, a charged particle that accelerates or changes direction should radiate energy in the form of electromagnetic radiation. This prediction was based on the Larmor formula, which describes the power radiated by a non-relativistic accelerating charge, P equals Q2 A2/60C3, where P is the power radiated, Q is the charge of the particle, A is the acceleration of the particle, 0 is the permittivity of free space, and C is the speed of light. According to classical theory, a charged particle, such as an electron in orbit around an atom, should radiate energy continuously as it accelerates in its orbit. This would cause the particle to lose energy, resulting in a gradual spiral inward and eventual collapse of the orbit. In fact, this would lead to the instability of the atom itself. However, experimental observations showed that atoms remain stable, with their electrons orbiting for extended periods without radiating away their energy. This contradiction between theory and observation became one of the key problems that quantum mechanics aimed to address. The solution emerged through quantum theory, which introduced the idea of quantized energy levels and the quantum nature of radiation. The paradox played a crucial role in the development of quantum electrodynamics, QED, and the Bohr model of the atom, ultimately leading to a new understanding of how charged particles interact with electromagnetic fields at small scales. The paradox of radiation of charged particles is one of the foundational issues in the development of quantum mechanics. It arises from the classical prediction that accelerating charged particles should radiate electromagnetic energy. This would result in the loss of energy by the particle, leading to an eventual collapse of the particle's motion. However, real-world observations showed that particles, especially electrons in atoms, did not behave as classical theory predicted. This contradiction pointed to the need for a deeper understanding of energy, motion, and radiation at the quantum level. 1. Classical electrodynamics and radiation of accelerating charges. A. Maxwell's equations and the Lama formula. Classical electrodynamics, as described by James Clerk Maxwell's equations, governs the behavior of electric and magnetic fields and how they interact with charged particles. According to Maxwell's theory, a charged particle that accelerates or changes direction generates fluctuations in the electromagnetic field, propagating outward as electromagnetic wave. The Lama formula predicts the radiation power of a non-relativistic accelerating charge, P equals Q, 2a2/60c3, where Q is the charge of the particle, A is the acceleration of the particle, 0 is the permittivity of free space, and c is the speed of light. According to this formula, any accelerating charged particle will radiate electromagnetic energy. The power radiated is proportional to the square of the acceleration, meaning that the faster the charge accelerates, the greater the energy radiated. B. The implication for accelerating electrons. In the classical picture, electrons in an atom are in orbits around the nucleus. These orbits involve acceleration, as the electron constantly changes direction. According to the Lama formula, the electron should radiate energy as it moves, causing it to lose energy and spiral inward. This would eventually lead to the electron falling into the nucleus, causing the atom to become unstable. The classical prediction suggests that an electron cannot remain in a stable orbit indefinitely, as it would lose energy through radiation and collapse into the nucleus, emitting energy in the process. This predicted instability is in stark contrast with the observed stability of atoms, where electrons appear to orbit the nucleus without spiraling inward. 2. The paradox. Observed stability versus classical predictions. A. The problem of energy loss. The paradox arises when we realize that the classical theory predicts that electrons in an atom should radiate electromagnetic energy as they accelerate in their orbits. The emitted radiation would carry away energy, causing the electron's orbit to shrink and eventually lead to orbital decay. In a matter of time, the electron would spiral into the nucleus, causing the atom to collapse. However, experiments showed that atoms were actually stable. The electron orbits did not decay over time, and atoms did not collapse. This contradiction between classical theory and experimental observations became one of the key problems in classical electrodynamics and led to the development of quantum mechanics. B. Stability of electrons in atoms. In atoms, electrons remain in stable orbits for long periods of time without radiating energy. The fact that atoms are stable, despite the predictions of classical electrodynamics, suggests that something is missing in the classical theory, a better understanding of how energy and radiation behave on small scales. This stability of atoms led to the development of the Bohr model of the atom, which introduced the concept of quantized energy levels. According to Bohr, electrons in an atom occupy specific quantized orbits and do not radiate energy as long as they remain in those orbits. End quote. Radiation occurs only when an electron jumps between these quantized orbits. 3. Quantum mechanics. The resolution of the paradox. A. The Bohr model and quantized orbits. The resolution of the paradox of radiation of charged particles came with the advent of quantum mechanics, and the development of the Bohr model of the atom. Niels Bohr postulated that electrons in an atom are confined to specific, quantized orbits around the nucleus. These orbits are associated with discrete energy levels, and an electron can only exist in one of these energy levels. According to Bohr's model, electrons do not emit radiation while in these quantized orbits. Radiation only occurs when an electron jumps between energy levels, and the energy difference between the levels is emitted as a photon. This approach solved the paradox by suggesting that electrons do not continuously lose energy in stable orbits, as classical theory predicted. Instead, they are confined to discrete orbits and only radiate when they transition between those orbits. B. The role of wave functions and quantization. The quantization of energy levels in the Bohr model was later extended and refined by the development of quantum mechanics. In quantum mechanics, the behavior of electrons is described by wave functions, which represent the probability of finding an electron in a given region of space. These wave functions are subject to quantization, meaning that only certain energy levels are allowed. In this quantum framework, the electron's energy is quantized, and it can only exist in certain stable states. The Heisenberg uncertainty principle also plays a role, as it suggests that we cannot simultaneously measure both the position and the momentum of an electron with arbitrary precision. This leads to the stability of electron orbits, as the electron does not radiate energy in a continuous manner. C. Quantum electrodynamics, QED, and virtual particles. Further developments in quantum electrodynamics, QED, provided a deeper understanding of the interaction between electrons and electromagnetic fields. In QED, the electron does not emit radiation simply because it is accelerating. Instead, the electron's interaction with the electromagnetic field is understood in terms of virtual particles, which mediate the electromagnetic force. These interactions are quantized, and electrons do not continuously radiate energy as predicted by classical theory. In QED, electrons can absorb or emit photons, quantized packets of electromagnetic radiation, only when transitioning between energy levels. The process is not continuous, and the electron's behavior is governed by the principles of quantum mechanics, not classical electrodynamics. 4. Implications of the paradox A. The need for quantum mechanics. The paradox of radiation of charged particles is a clear example of the limitations of classical mechanics in explaining the behavior of particles on small scales. The paradox illustrates the need for a new framework, quantum mechanics, to describe the stability of atoms and the discrete nature of energy levels. Without quantum mechanics, the classical predictions about the radiation of charged particles would lead to the instability of atoms, which clearly does not match experimental observations. B. The unification of electromagnetism and quantum theory. The paradox also highlights the need to reconcile electromagnetism with quantum theory. Classical electrodynamics alone cannot explain the stability of atoms, while quantum mechanics provides a complete and consistent framework for understanding how charged particles interact with electromagnetic fields. The development of quantum electrodynamics, QED, unified quantum theory and electromagnetism, providing a more accurate description of particle behavior and radiation. Quantum field theory and the nature of radiation. The paradox of radiation of charged particles laid the groundwork for understanding the nature of radiation in quantum field theory. In QED, radiation is not a continuous process, but rather a series of quantized interactions between particles and fields. This understanding of radiation as a quantized phenomenon resolved the paradox and helped establish the foundation of modern quantum electrodynamics. Supple's paradox. Imagine a quantum system where two seemingly independent events occur simultaneously, each one containing a certain degree of uncertainty. You can predict the probability of each event, but the combination of these events leads to a paradoxical conclusion that contradicts classical intuition. This is the essence of Supple's paradox, a thought experiment that explores the strange interactions between uncertainty, probability, and decision-making in quantum mechanics. The paradox arises when independent events are thought to be mutually exclusive, yet their combination leads to an outcome that seems to violate the basic principles of information theory. How can events, which are traditionally seen as independent in classical physics, interact in a way that causes an outcome more complicated than expected? Supple's paradox challenges our classical notions of information and independence in quantum systems. leading us to rethink how decisions are made in the presence of uncertainty. What does this paradox tell us about the relationship between information, uncertainty, and quantum states? Let's explore the Ship Paradox, where independence and uncertainty converge in a puzzling and profound scenario that forces us to reconsider how quantum systems behave. Ship Paradox was introduced by the American physicist Robert Ship as part of his work on quantum systems and their relationship with information theory. The paradox emerged from a thought experiment designed to explore the concept of uncertainty and how it manifests in the context of quantum mechanics. Specifically, the paradox examines how the uncertainty principle, which states that we cannot simultaneously know certain pairs of properties, like position and momentum, with arbitrary precision, can lead to counterintuitive conclusions in quantum systems. While quantum mechanics is well known for its ability to describe systems with a degree of indeterminacy, Ship's paradox presents a scenario in which this uncertainty leads to surprising interactions between independent events. The paradox highlights the tension between classical and quantum notions of independence and decision-making, showing how quantum uncertainty can lead to outcomes that violate classical expectations. The paradox is part of ongoing efforts in quantum information theory, where physicists are working to understand how information behaves in quantum systems, especially in contexts where uncertainty and decision-making processes are involved. The Ship paradox has sparked discussions about the nature of independence in quantum systems and how we model uncertainty when making decisions in such systems. The Ship paradox arises from the tension between classical and quantum understandings of uncertainty and independence. It is a thought experiment that explores how the combination of uncertain events in a quantum system can result in paradoxical outcomes, forcing us to reconsider basic concepts of decision-making, information, and probability. The paradox provides insight into the behavior of quantum systems, where uncertainty is not just a limitation of measurement, but a fundamental feature of the system itself. 1. Classical understanding of uncertainty and independence. A. Classical uncertainty and probability. In classical physics, uncertainty is often viewed as a lack of knowledge or measurement error. When two events are independent in a classical context, the outcome of one event has no effect on the outcome of the other. The probability of both events occurring is simply the product of the probabilities of the individual events. PA and B equals PAX, PBB. This is a straightforward application of probability theory, where the two events are independent, and the total probability of their occurrence is the product of their individual probability. Classically, we might think of two dice being rolled. The outcome of one die has no effect on the outcome of the other, so the probability of both dice landing on a particular number is the product of their individual probabilities. This independence holds true for classical systems, where uncertainty is treated as a limitation in knowledge, rather than an inherent feature of the system. Classical decision-making and information. In classical decision-making, we make predictions based on known probabilities. If two events are independent, we can simply multiply their probabilities to determine the likelihood of both events occurring. In the case of independent decision-making, each choice has an equal and non-interfering effect on the other. Classical information theory also assumes that the information about each event can be known precisely, and that uncertainty arises only due to limitations in measurement or external factors. The decision-making process in a classical system is governed by deterministic principles and independent assessments of each event's probability. 2. Quantum uncertainty and the superposition principle. A. The uncertainty principle. In quantum mechanics, uncertainty takes on a more fundamental role. The Heisenberg uncertainty principle states that certain pairs of properties, such as position and momentum, cannot both be known with arbitrary precision. The more precisely one property is measured, the less precisely the other can be determined. This principle suggests that the uncertainty is not a result of measurement limitations, but a fundamental feature of quantum systems. Particles do not have definite positions and momenta until they are measured. Instead, they exist in a superposition of possible states. The uncertainty principle reflects this probabilistic nature of quantum systems, where the state of a system is described by a wave function that gives the probability of finding a particle in various states. The superposition principle, in quantum mechanics, further complicates our understanding of uncertainty. A particle can exist in multiple states simultaneously, and only when measured does it collapse into one of the possible states. This creates a different relationship between independent events in quantum mechanics compared to classical physics. B. Quantum interference and superposition. In quantum systems, events that are normally independent in classical systems can interfere with each other due to the principle of quantum superposition. For instance, a particle can be in a superposition of two possible states at once, and these states can interfere with each other, producing outcomes that are not simply the product of the probabilities of the individual events. This interference effect is a key feature of quantum mechanics and leads to counterintuitive results. The combination of two independent quantum events does not simply follow classical rules of probability multiplication, and this introduces a level of complexity in quantum decision-making that classical systems do not exhibit. C. Quantum entanglement and correlation. In quantum mechanics, entangled particles are another source of uncertainty and paradox. When two particles become entangled, their properties are linked in such a way that the measurement of one particle's state instantly affects the state of the other, regardless of distance. This non-local correlation contradicts classical intuition, where independent events do not influence each other across space. In the case of quantum decision-making, entangled particles can produce results that appear non-local and instantaneous, leading to paradoxical outcomes when viewed through the lens of classical probability. The correlation between entangled particles creates a scenario where information about one particle's state is inherently linked to the other, defying the classical principle of independence. 3. The Supplet paradox, combining uncertainty and probability. A. The setup of the paradox, Supplet's paradox, involves a quantum system where two independent events occur, each with its own uncertainty and probability. These events are combined in a way that the quantum system does not follow classical rules of probability and independence. The paradox typically involves two processes or systems that should be independent according to classical mechanics, but when treated quantum mechanically, their combined effect leads to an outcome that is inconsistent with classical intuition. In classical systems, the outcome would simply be the product of their probabilities, but in the quantum world, the interference effects and the uncertainty principle make the situation much more complex. The uncertainty in the quantum system leads to correlations between the events that would not be present in classical systems, and this results in a non-classical outcome. This can lead to apparent contradictions or paradoxes when we attempt to apply classical reasoning to the quantum system. B. The role of information and measurement. The paradox also brings into question the role of information in quantum systems. In classical systems, information is treated as a deterministic variable, and we can calculate the probability of outcomes based on known information. However, in quantum systems, the act of measurement itself disturbs the system, and the uncertainty is not just a limitation of our knowledge, but a fundamental feature of the system. Supplet paradox shows that the information about the system is not simply a collection of known variables, but is subject to the quantum uncertainty principle. This challenges classical ideas of decision-making and probability, where information about an event can be precisely known and used to make predictions. 4. Resolution of the paradox, quantum mechanics and the nature of information. A. Quantum decision-making and uncertainty. The resolution of Supplet's paradox lies in the recognition that quantum systems operate according to the principles of quantum mechanics, where uncertainty and interference play key roles. The paradox shows that in the quantum world, events that are independent in classical systems can become correlated due to the principles of superposition and entanglement. The paradox emphasizes that in quantum systems, the relationship between independent events is not governed by classical probability theory. Instead, the outcomes are influenced by the wave function of the system and the interference effects between possible states. The probabilistic nature of quantum mechanics makes the decision-making process more complex than classical theory would suggest. B. The nature of information in quantum systems. Supplet's paradox also points to the deeper nature of information in quantum mechanics. Unlike classical systems, where information can be treated as a known variable, quantum systems require a different understanding of how information is stored, transmitted, and measured. The uncertainty principle and the wave function collapse are intrinsic to how information behaves in quantum mechanics, leading to a fundamentally different approach to decision-making and probability. Tachyonic anti-telephone paradox. Imagine being able to send information faster than the speed of light, perhaps to the past, In the realm of special relativity, this is strictly prohibited because nothing can travel faster than light. However, the concept of tachyons, hypothetical particles that always travel faster than light, introduces a strange and paradoxical twist. What if you could use tachyons to send signals back in time, creating an anti-telephone that allows you to communicate with the past? The tachyonic anti-telephone paradox arises from the implications of such a device. While it theoretically violates causality, it could also be used to send messages to a past observer. But this leads to a major conundrum. If you can communicate with the past, would sending information back in time create a causal loop, a situation where the past is altered in such a way that it creates contradictions or even paradoxes, like the grandfather paradox? How does relativity and our understanding of causality hold up in the face of such a possibility? Let's explore the tachyonic anti-telephone paradox, where faster-than-light communication and causal loops collide in a mind-bending challenge to our understanding of time and space. The concept of a tachyonic anti-telephone arises from the idea of tachyons, hypothetical particles that travel faster than light. The term was first introduced in the context of theoretical physics, and the tachyonic anti-telephone paradox is a thought experiment built upon the implications of these particles in special relativity. Special relativity, introduced by Albert Einstein in 1905, posits that nothing can travel faster than the speed of light in a vacuum, and this imposes a strict limit on the speed at which information can travel through space. Tachyons, however, are theoretical particles that always travel faster than light and have the peculiar property that their energy increases as their speed decreases. The possibility of using tachyons to send information faster than light, and potentially even backward in time, creates the paradox. The tachyonic anti-telephony paradox considers the implications of a device that could allow for faster-than-light communication, raising questions about causality and time travel. The paradox itself stems from the grandfather paradox, a common issue in time travel scenarios, where the ability to send information to the past could result in contradictions. The paradox explores whether the possibility of tachyonic communication could break the very fabric of causality and lead to situations where the timeline is altered in an infinite loop or even erased. The tachyonic anti-telephone paradox is a thought experiment that explores the consequences of faster-than-light communication using tachyons, particles that always travel faster than light. This paradox highlights the conflict between the laws of special relativity, which prohibit faster-than-light communication, and the idea of time travel and causality. By sending signals to the past, the tachyonic anti-telephone creates a scenario that may lead to causal loops and paradoxes, leading us to reconsider our understanding of space-time, causality, and the possibility of time travel. 1. Special relativity and the speed of light A. The principle of relativity and special relativity, the speed of light, c, is the universal speed limit. This means that no information or object can travel faster than c. This principle is central to Einstein's theory of relativity and is supported by extensive experimental evidence. According to special relativity, any signal or particle that travels faster than light would violate the laws of causality, as it would allow for the possibility of sending information backward in time. The speed of light serves as the upper bound for the speed at which any information or influence can propagate. If something could travel faster than light, it could reach an observer before it was emitted, which could cause situations where an event occurs before its cause. This creates the potential for paradoxes, where events can be out of order in time, leading to contradictions. B. Tachyons. Hypothetical particles. Tachyons are hypothetical particles that have an imaginary mass and are theorized to always travel faster than light. In special relativity, these particles have the peculiar property that they can never slow down to below the speed of light, and their energy increases as their speed decreases. This is in stark contrast to particles with real mass, which gain energy as they accelerate, but cannot exceed the speed of light. Tachyons were first proposed in the context of theoretical particle physics, and were considered to have unusual mathematical properties. While they are not part of the standard model of particle physics, they are still discussed in the context of certain quantum field theories and have interesting implications for causality and the structure of spacetime. 2. The tachyonic anti-telephone, FTL communication and time travel. A. The concept of the anti-telephone, The tachyonic antitelephone is a thought experiment that involves using tachyons to send signals faster than light. Imagine an observer at point A who sends a signal to point B using tachyons. Because tachyons travel faster than light, the signal will reach point B before it is even sent, theoretically arriving at point B before it is emitted from point A. This leads to the possibility of time travel, in the sense that information can be sent into the past. If the signal arrives at point B before it is sent from point A, then an observer at point B could receive the message before point A has even sent it. This creates a time paradox, as the signal appears to be received before it was ever sent. B. Causal loops and paradoxes. The tachyonic antitelephone paradox arises when we consider the implications of using tachyons to send messages to the past. If information can be sent back in time, it raises questions about the nature of causality. In the case of the tachyonic antitelephone, a message sent to the past could change the very conditions under which the message was originally sent, leading to a causal loop. A causal loop occurs when an event in the future influences an event in the past, which then leads to the same event in the future. For example, a message sent via the tachyonic antitelephone could alter the behavior of the sender in the past, causing them to send the message in the first place. This leads to an infinite loop where the message is constantly sent back and forth in time. One well-known example of this type of paradox is the grandfather paradox, where a person travels back in time and prevents their own grandfather from meeting their grandmother. This would prevent the time traveler from ever being born, leading to a contradiction in the timeline. C. Violating causality. The primary issue with the tachyonic antitelephone paradox is that it violates causality. In classical physics and special relativity, causality is a fundamental principle. The cause must precede the effect. If information can travel back in time and affect past events, this leads to situations where the cause and effect become unclear or reversed. This causal violation creates logical contradictions. For instance, if a message is received before it is sent, the sequence of events becomes scrambled and the timeline becomes unstable. The paradox challenges the fundamental structure of time as we understand it, forcing us to reconsider the possibility of time travel and faster-than-light communication. 3. Possible resolutions to the paradox. A. The Novikov self-consistency principle 1, potential resolution to the tachyonic antitelephone paradox, comes from the Novikov self-consistency principle. This principle suggests that events in the universe are self-consistent, meaning that if time travel is possible, the laws of physics will prevent any actions that would lead to contradictions. In the case of the tachyonic antitelephone, the principle would ensure that the message sent into the past could not change the past in a way that would prevent the message from being sent in the first place. This principle would prevent the creation of paradoxes, such as the grandfather paradox, by ensuring that any event that could lead to a causal loop would be forbidden by the laws of physics. The self-consistency principle essentially imposes limits on the types of changes that can be made to the past, allowing time travel without violating causality. B. The many worlds interpretation. Another potential resolution comes from the many worlds interpretation, MY, of quantum mechanics. According to MWI, every possible outcome of a quantum event creates a branching universe in which each possibility is realized. If a message is sent into the past using the tachyonic antitelephone, the many worlds interpretation would suggest that the timeline splits into multiple parallel universes, each with its own version of events. In this view, sending a message into the past would not cause a paradox, as it would create a new timeline in which the events unfold differently. The original timeline remains unchanged, and the new timeline follows the altered path. This avoids the violation of causality and allows for the consistent existence of time travel. C. Closed time-like curves. Closed time-like curves, CTCs, are another concept from general relativity that could offer a resolution. CTCs describe paths in spacetime that return to the same point in time, creating loops that allow for time travel. However, these loops would be constrained by the geometry of spacetime, and the laws of physics would prevent contradictions from arising. In the context of the tachyonic antitelephone, CTCs would allow information to travel backward in time without causing paradoxes, as the loop would be constrained by the structure of spacetime. This theory suggests that time travel is possible, but only in a way that does not violate causal relationships. True to Noble paradox. Imagine a charged, conducting body that is suspended in space, with the electric field of the body oriented in a particular direction. According to classical electromagnetism, if the body is moving through space, the Lorentz force should act upon it, causing a torque to appear. This would lead the body to experience a twisting force, even though there is no external force acting on it. This is the essence of the Troughton-Noble paradox. It suggests that a moving, charged conductor should experience a torque due to the interaction between the electric field and the motion of the object, even though no such torque seems to be observed in practice. The paradox challenges our understanding of how electromagnetic forces behave when objects move relative to a field, especially when considering classical electromagnetism. How can a charged object moving through space with a given electric field not experience the predicted torque? This paradox raises important questions about the nature of force in moving systems and the principles of relativity. Let's explore the Troughton-Noble paradox, where motion, electromagnetism and torques collide in a thought-provoking puzzle about the nature of forces and their effects on moving bodies. The Troughton-Noble paradox was first described in 1901 by physicists F. Troughton and H. Noble. It arose from an experiment designed to test the behavior of a charged conductor in a uniform electric field. In the experiment, the conductor was suspended and allowed to rotate in a magnetic field. According to classical electrodynamics, when a charged conductor moves through a magnetic or electric field, a torque should be exerted on it due to the interaction between the field and the moving charges within the conductor. However, the results of the experiment showed that no torque was observed, even though the setup seemed to meet all the conditions for generating such a torque. The discrepancy between the theoretical prediction and the experimental result led to the formulation of the Troughton-Noble paradox. The paradox suggests that classical electromagnetism, when applied to moving charged bodies, predicts the existence of a torque that does not seem to manifest in practice. This paradox raised important questions about the nature of forces in electromagnetic systems and whether the principles of special relativity or Lorentz transformations could offer a better understanding of the interaction between electric fields and moving objects. The resolution of the paradox would ultimately contribute to the development of a more refined understanding of electromagnetic theory, as well as the role of relativity in the description of forces and motion. The Troughton-Noble paradox is a thought experiment that exposes a contradiction between the predictions of classical electromagnetism and experimental observations in the context of charged bodies in motion. The paradox centers around the idea that a moving charged conductor should experience a torque due to its motion through an electric field, but no such torque is observed in practice. This paradox is not just a theoretical puzzle, but a challenge to our understanding of forces and motion in electromagnetic systems, especially when applied to systems in motion relative to a field. 1. Classical electromagnetism and the setup of the paradox. A. Electric and magnetic forces in classical mechanics. In classical electromagnetism, the interaction between charged particles and electromagnetic fields is described by Maxwell's equations, which govern the behavior of electric and magnetic fields and their interaction with matter. The Lorentz force law describes the force experienced by a charged particle moving through an electromagnetic field. F equals QE plus V, XB F equals QE plus V, where FF is the force on the particle, QQ is the charge of the particle, EE is the electric field, BB is the magnetic field, VB is the velocity of the particle. According to the Lorentz force law, when a charged particle moves through a magnetic or electric field, it experiences a force proportional to its velocity and the field's strength. In the case of a charged conductor moving through an electric field, the individual charges within the conductor should experience forces that lead to a torque on the entire object. B. The Troughton-Noble experiment setup. The Troughton-Noble experiment involved suspending a charged conductor in an electric field and observing its behavior. According to classical theory, if the conductor is in motion relative to the electric field, the moving charges within the conductor should experience forces that generate a torque. This torque would cause the conductor to rotate as the electric field interacts with the moving charges. The setup seems straightforward, and according to the Larmor formula and Lorentz force law, the moving charges should radiate energy and produce a torque on the system. However, no torque was observed in the experiment, leading to the apparent contradiction that became the Troughton-Noble paradox. 2. The paradox. Why is no torque observed? A. Classical predictions of torque. In classical electrodynamics, when a charged conductor moves through a magnetic or electric field, the individual charges experience forces that should lead to a torque on the conductor. The torque arises due to the Lorentz force acting on the moving charges, and it would cause the conductor to rotate. This is the expected behavior according to classical theory, which predicts that the torque should be proportional to the charge, the velocity of the conductor, and the strength of the electric field. In the Troughton-Noble experiment, however, no such torque was observed, even though the setup seemed to fulfill the conditions for torque generation. The absence of the expected torque creates a paradox in classical electromagnetism, as the predictions do not match the experimental results. B. The role of relativity. The Troughton-Noble paradox suggests that the classical treatment of moving charged conductors and their interactions with electric fields might be incomplete. The absence of torque is difficult to explain using the classical Lorentz force law alone, and this indicates that something deeper might be at play. Special relativity comes into play when considering the motion of the charged conductor. According to relativity, the electric field of a moving charged particle is not the same as the electric field of a stationary particle. The motion of the charged conductor would alter the distribution of the electric field and could change the interaction between the field and the moving charges in such a way that the predicted torque is not realized. In relativity, the electric field of a moving charge becomes part of a combined electromagnetic field, which also includes a magnetic field due to the motion of the charge. This change in the structure of the field leads to different force interactions than those predicted by classical electromagnetism. C. Relativistic treatment of the paradox. When the moving conductor is treated relativistically, the behavior of the electric field changes, because the moving charges create a relativistic electromagnetic field that affects the force on the conductor. The relativistic theory accounts for the time dilation and length contraction that occur at high velocities, and this leads to a different result than the one predicted by classical electromagnetism. In the relativistic view, the absence of torque in the Troughton-Noble experiment can be explained by the fact that the electric field and the magnetic field of the moving conductor combine in a way that does not generate a torque on the object. This relativistic treatment resolves the paradox by showing that classical electromagnetism does not fully account for the effects of relativity on the electromagnetic interaction. 3. Relativistic electromagnetic theory and torque generation. A. The role of the field transformation. In relativistic electrodynamics, the transformation of the electromagnetic field from one frame to another is more complicated than the simple application of the Lorentz force. When the conductor moves through the electric field, the interaction between the conductor and the field is affected by the relativity of simultaneity and electromagnetic field transformations. The combination of the electric and magnetic fields changes when viewed from different frames of reference. The electromagnetic field of the moving conductor is not simply the sum of the fields of its individual charges, but rather a relativistic combination of electric and magnetic fields that produce forces in a manner consistent with special relativity. These relativistic field transformations prevent the generation of a torque in the Troughton-Noble experiment. The electrodynamics of moving bodies in the relativistic view, the interaction between the electric field and a moving conductor must be understood in terms of the combined electromagnetic field, which is a manifestation of the unification of electricity and magnetism in special relativity. The field generated by a moving charge is not purely electric, but also includes a magnetic component. As a result, the predicted torque does not appear because the forces from the electric and magnetic fields cancel out or modify each other in a way that does not result in rotational motion. 4. Implications of the paradox A. The incompleteness of classical electromagnetism. The Troughton-Noble paradox highlights the limitations of classical electromagnetism when applied to moving bodies, especially at high velocities. The paradox suggests that classical theory does not fully capture the relativistic effects on the interaction between charged particles and electric fields, leading to unexpected results, like the absence of the predicted torque. B. Relativity and electromagnetic interactions. The resolution of the paradox relies on special relativity, which provides a more accurate framework for understanding how charged particles interact with electromagnetic fields in motion. The unification of electric and magnetic fields in relativistic contexts leads to different force interactions than those predicted by classical electrodynamics, providing a more complete understanding of electromagnetic forces in moving systems. C. The role of Lorentz invariance. The paradox also emphasizes the importance of Lorentz invariance in the behavior of electromagnetic fields and forces. The forces that a charged conductor experiences are frame-dependent, and special relativity shows that the interaction between the conductor and the field depends on the relative motion between the system and the observer. This introduces a level of complexity that classical electromagnetism does not fully account for. Twin paradox. Imagine two twins, Anna and Ben, who are exactly the same age. Anna stays on Earth, while Ben embarks on a journey through space, traveling at a high speed close to the speed of light. When Ben returns to Earth after his journey, something strange happens. He is younger than Anna, despite both twins being the same age when they parted ways. According to special relativity, time passes more slowly for objects moving at high speeds, a phenomenon known as time dilation. Ben, traveling close to the speed of light, experiences less time than Anna, who remains on Earth. This is the twin paradox, a thought experiment that challenges our intuitive understanding of time and aging. How can two individuals in the same starting state experience different passage of time? Is it possible for one twin to age more slowly than the other, despite both observing each other from their own perspectives? Let's dive into the twin paradox, where time dilation, relativity, and simultaneity collide in a thought-provoking puzzle that reveals the counterintuitive nature of spacetime. The twin paradox is one of the most famous thought experiments in special relativity, first presented by Albert Einstein in his theory of special relativity in 1905. The paradox arises from the predictions of time dilation, a key aspect of Einstein's theory, which states that time passes more slowly for objects moving at high speeds relative to an observer at rest. The thought experiment involves two identical twins. One twin, say Ben, travels on a high-speed journey through space, while the other twin, Anna, remains on Earth. According to special relativity, Ben's clock will run slower due to his motion, meaning that he will age less than Anna during the trip. Upon Ben's return, he will be younger than Anna, despite both twins having been the same age when they parted ways. At first glance, the twin paradox seems like a contradiction. From Anna's perspective, Ben is moving at a high speed and should be experiencing time dilation. But from Ben's perspective, it is Anna who is moving, so it would appear that she should be the one experiencing time dilation. The paradox arises from the apparent symmetry of the situation. Both twins seem to see the other as moving and should expect them to age more slowly. The resolution of the paradox lies in the fact that the situation is not symmetric. Ben's journey involves acceleration and deceleration, changing reference frames, which breaks the symmetry and explains why he ages less than Anna. The relativity of simultaneity and the effects of acceleration play key roles in the resolution of this paradox. The twin paradox is one of the most striking and puzzling thought experiments in special relativity. It forces us to rethink our intuitive understanding of time and how it is experienced by observers in different frames of reference. The paradox is rooted in the concept of time dilation, a phenomenon where moving clocks tick slower than stationary clocks from the perspective of a stationary observer. However, the paradox arises from the apparent symmetry of the situation, as both twins see the other as moving. So why is Ben younger than Anna when they reunite? 1. The basics of special relativity and time dilation. A. Time dilation in special relativity, at the heart of the twin paradox, is the concept of time dilation. According to Einstein's theory of special relativity, the faster an object moves relative to a stationary observer, the slower its clock will appear to tick from the perspective of the observer. This phenomenon is not due to a malfunction of the clock, but a result of the way time and space are interwoven in relativity. The formula for time dilation is given by the Lorentz factor, d equals det/1 v2/c2, where dt is the time interval as measured by the moving object in Ben's case, dt is the time interval measured by the stationary observer in Anna's case, v is the velocity of the moving object, Ben's spaceship. B is the speed of light. For objects moving at speeds close to the speed of light, This formula shows that the time interval measured by the moving observer, Ben, will be much longer than the time interval measured by the stationary observer, Anna. This means that Ben will age more slowly than Anna while he is traveling at high speed. B. The symmetry of the situation. The paradox arises from the apparent symmetry of the situation. Both Ben and Anna can observe each other's motion. From Anna's perspective, Ben is traveling at high speed and his clock is running more slowly. But from Ben's perspective, it is Anna who is moving at high speed and her clock should be running more slowly than his. Classically, we might think that both observers should experience the same amount of time dilation. However, the key insight of special relativity is that the situation is not symmetric. Only Ben's journey involves acceleration and deceleration. This breaks the symmetry and explains why Ben, not Anna, will age more slowly. 2. Resolving the paradox. The role of acceleration. A. The effect of acceleration. The key difference between the two twins' experiences is that Ben's journey involves acceleration, while Anna remains at rest on Earth. In special relativity, only inertial reference frames, those not undergoing acceleration, are treated symmetrically. When Ben turns around at the far end of his journey to return to Earth, he accelerates to change direction. This acceleration breaks the symmetry of the situation, as Anna remains in a single inertial frame throughout the experiment. The acceleration causes Ben's reference frame to change, which introduces an asymmetry between the two observers. In other words, Ben's experience of time is affected not just by his speed relative to Anna, but also by the fact that he changes reference frames during his journey. B. The relativity of simultaneity. Another important concept in resolving the paradox is the relativity of simultaneity, which states that two events that appear simultaneous in one reference frame may not appear simultaneous in another reference frame, moving relative to the first. For example, when Ben is moving at high speed relative to Anna, he perceives the passage of time differently than Anna does, and this includes how he perceives simultaneous events in Anna's frame. The relativity of simultaneity means that even though both twins experience time passing, they do not agree on what events happen simultaneously. When Ben changes direction at the farthest point of his journey, his frame of reference shifts, and he effectively recalculates his view of simultaneous events in Anna's frame. This shift is critical because it causes the age discrepancy between the twins when they reunite. 3. Why Ben ages more slowly? The complete explanation. A. Time and space in different frames. According to special relativity, time is not absolute. It depends on the observer's relative motion. In the case of the twins, Anna and Ben measure time differently due to their relative velocities. However, the crucial difference is that Ben, by undergoing acceleration during his journey, changes his reference frame. As a result, the time dilation he experiences is different from Anna's. Even though both twins see each other as moving, Ben's experience of time is fundamentally different due to the non-inertial frame he occupies while traveling. This is why, when the twins reunite, Ben will have aged less than Anna, despite both twins observing the other as moving during the trip. B. The distance between the twins. At the moment Ben turns around to return to Earth, Anna perceives his clock to be ticking slower. Meanwhile, Ben, upon returning, perceives Anna's clock to be ticking slower. However, this perception doesn't lead to a paradox, because the acceleration Ben undergoes alters the way he experiences time. In essence, the total elapsed time for each twin is different because of the difference in the paths they follow through space-time. 4. Implications of the paradox. A. The concept of space-time, the twin paradox, illustrates a fundamental feature of special relativity, that time and space are not separate entities but are interconnected in space-time. Time dilation, as seen in the paradox, is a consequence of the geometry of space-time, where the passage of time for an object depends on its velocity and its position in the curved space-time B. The nature of causality, the resolution of the twin paradox, also highlights how special relativity preserves causality in scenarios involving time dilation. Even though one twin ages more slowly than the other, the relationship between cause and effect remains intact. The paradox does not involve any violation of causality, but rather shows how time itself behaves differently depending on the relative motion of observers. C. The role of acceleration. The role of acceleration is critical in breaking the symmetry of the situation. This is because the accelerated twin, Ben, is not in a uniform inertial frame of reference. The transition from one reference frame to another during his journey introduces an asymmetry that explains the different aging rates for the twins.